attendance. This is surprising, but I mean, everyone is welcome. The room is definitely big enough to accommodate everyone. So yeah, it's an extremely big attendance, and we also got a lot of papers for the conference. I mean, not papers, but talks. So this was also surprising and pretty new to us. So yeah, we've been lucky enough that we only refused a few talks. So we just had a tight schedule, so maybe for future years we will start thinking about extending the conference a bit, especially if it's supposed to last like this, being above, well, last time I checked it was 117 people, so usually the attendance is about 60. That's twice as much, twice as many. So yeah, this conference has also something that is pretty new is that there's a lot of talks about the windowing system integration. This is not something we usually talk about a lot, but it definitely proves that there's a lot of changes in this direction, and this is good. So we have the entire first day just for windowing system integration, and with one very big issue, which is the Unix memory allocation problem that we've been trying to solve for years. And luckily we managed to get people from different companies to work on this, and really, I would really love to see this problem solved by the end of the conference. This is a tough challenge, but I believe in you. I mean, if not now, then when? So at the end of the conference, we're going to have lightning talks. So everything that you would have discussed during the conference and you would like to report on, you should do it at the end. So it's basically a 5-minute presentation, and we'll have 6 slots at the end. So definitely do come up with ideas and of discussions or anything that you had. Create one slide of it, send it to me before the lightning talks, and yeah, we should be good to go. And so I at least expect one. Guess which one? And yeah, hopefully there's going to be more. Then, as for the internet and power, there is a power adapter at every sit. So just under you should be able to plug your laptop or whatever you want to plug. For the internet, you need to send WLAN to this phone number that you have here. If it's too small, I think you can always just connect to this one, and they will give you instructions on how to do this. The last digit is a 5. I can, rewrite this one. Yeah, I can try to rewrite it after talking. The next thing is the social event. Okay. Well then, yeah, if you have any trouble with getting the internet, we'll try to find some solution for you. Yeah, the last thing is social event. So on Saturday, for everyone staying here, we are going to have a social event. We don't know yet what we're going to do, but it's probably going to be visiting parts of Helsinki and then going to a sauna and dipping yourself in the sea. So something like this. Right now the sea temperature is about 14 degrees, still acceptable. And yeah, so definitely I need to know by the end of the day who's coming. So I'll set up probably a list and then just write your name on it, just to get an estimate, and then I'll try to come up with something to do that would accommodate all these people. Okay, well, I don't know what else I could have forgotten, but yeah. Yes, Chad? What time are we taking the dip in the ocean? So the question is, what time are we taking the dip in the ocean? Probably around 5. Why? Okay. Yeah. Well, 5 a.m. of course. Yeah. Well, have a good conference, and thanks again for coming. So the first presenter should come now and set up the machine. So it was the hardware DRM, the DRM hardware composer.
Have you remembered your... Hello? Can you hear me? Yep. Excellent. Is yours on? (9:30). for its massive size.
So yeah, do not text this actually. We're gonna have another solution soon. Yeah, so we can just turn the sheet and be done with it. So yeah, we're gonna get something, and sorry for the delay. And basically you have 3 more minutes to wait, and then you can start.
know if it's working. Oh, is it working? Is yours working? I don't know. Hello?
Hello? Oh.
Hello?
What?
Are we roughly the same volume?
It's very touchy.
Okay.
Okay, I think we're ready to start. Hi, I'm Sean, and this is Zach. We work on the Chrome OS team at Google, and we're here to talk about DRM Hardware Composer. So what is Hardware Composer? Probably most of you already know this, but it's hardware abstraction layer that sits in between Android user space Surface Flinger and the display driver that's for whatever device. So DRM Hardware Composer is an implementation of Hardware Composer that sits on top of DRM KMS. How does that work? So just a quick overview of the timeline. We started development in January 2015 for this. It was a pretty thin C implementation, and we used a test harness that basically emulated Surface Flinger and got a bitmap on screen, and that was sort of the first step. We didn't have sync points or anything like that. After that, we moved to C++, and we sort of wrapped libdrm and some of the more tricky, I guess, ioctls and property handling became a lot easier when we switched to C++. It also reduced the number of calls we had to make for things that we knew weren't changing. Once we had that sort of working, Zach converted a lot of it to C++11 classes to make things a bit safer. So we had a bunch of closes and frees and that type of thing sprinkled through the code. And with the resource management features that C++11 offered us, we were able to get rid of those and basically guarantee that we wouldn't get into fence timeouts or deadlock, that type of thing. We also added a GL compositor to the Hardware Composer, and that was basically allowed us to squash parts of the screen and the entire screen to improve performance and improve power management, that type of thing. And that's what we shipped with the Pixel C tablet in December of 2015 with Android M. After that, in preparation for Android N, the new multi-window support came in, and it exposed a bunch of assumptions that we made, I guess, about how Surface Flinger gave us layers. And we had to introduce a planner which allowed us a bit more flexibility and control with respect to how we map layers from Surface Flinger to overlays on the hardware. And then Zach also implemented a Vulkan compositor to sit beside the GL compositor, replace the GL compositor. So this is what we have. This is DRM Hardware Composer, I guess, at a high-level view. So you can see Surface Flinger at the top takes a stack of layers, or gives a stack of layers to our interface point, which is the DRM Hardware Composer. And that pushes those layers into what we call the DRM compositor, which then sort of splits those up per display. So the stack from Surface Flinger is all the layers across all of the displays. So it splits it per display and then passes it into what we call DRM display compositor, which then goes into a queue, which is that little arrow right here. And so the green box is a thread. So that whole thing happens within one thread. It goes into a queue, and then eventually another thread called the DRM composer worker picks it up, and it does. It waits for all of the relevant fences to signal, which means it can actually then put it on the screen. Once all of that signals, then it goes into yet another thread called the frame worker, which is what actually does the DRM commit and puts it on the screen. So it's super convoluted and not exactly simple, but we'll get to how we make the world better later.
So just to dive into a little bit of the details, for those of you who maybe want to look at the code or contribute to it, I was going over a quick code overview. We saw kind of conceptually how it works, but I wanted to go over a few more details. So the first thing that happens for Hardware Composer is that it's loaded as a shared object from Surface Flinger, and it calls hwc device open inside of our Hardware Composer. And at this point, we do initialization, DRM resources, init. That loads all of the DRM properties, literally calls DRM get resources, gets all the property blobs, various things that, like you said, don't change, but we need them all the time. And this really helped us, organize things a bit better. And also initializes a compositor, and the DRM compositor is shared for everything the Hardware Composer does. And it, in turn, will, for each connector, create a display compositor. This tended to cause a bit of confusion going through the code. Just know that there is a DRM compositor and a DRM display compositor. The top level, yeah, it's not the right one. How is it? There we go. The top level one really just organizes a gang of display compositors per connector. For the base pixel C, there's really only just one for the internal display. It also generates our platform support modules, the planner that I mentioned before. This helps with some stuff I'll get to in a minute, and the importer, which takes the basically Android's native types for buffers and turns them into buffer objects, standard DRM type stuff. That's also platform specific, and that's created at init time. Yeah, so there's a lot of stuff on the screen, and I'll try to get through it quickly. We kind of showed you the high-level overview a couple slides ago, so just kind of try to keep that in your head a little bit while we're also looking at this. So the first thing we do, and this is really important aspect because we had reliability problems a lot at the beginning, is encapsulate everything in our C++ types. We use standard, the move semantics, all sorts of, unique ownership style of C++ coding, basically just to make sure we clean up in case of any failure. This is the first thing we do, and we ensure the step has no errors or can't fail. And if it does fail, we don't return yet. We make sure to finish encapsulating everything, so that way all the fences get signaled, all of them get closed, a lot of them are FDs, buffers get freed, everything, in case of any kind of failure. And it's turned into a display composition, which is sort of our big object for basically one frame's worth of thing for every display. Every display shares the one DRM composition. So yeah, we assign around that, right? Yeah. Assign release fences because HWC. Oh, I forgot to mention HWC set is called also by Surface Flinger. So this is sort of the meat of our HWC is done in this function, an HWC set. And we're given a bunch of contents, and one of the things we have to do as part of the contract with Surface Flinger is assign release fences, which I mentioned right there. So we create a composition, which doesn't really do much, just kind of creates an empty object, and then we assign it layers. And even at this point, not a whole lot's happening. We're just kind of doing bookkeeping at this point, assigning layers to various sub-compositions and whatnot. The real sort of, I guess, first piece of meat to our meat compositor. I don't know where I'm going with this. But we, this is where we actually start planning things. And we do this for a reason, and that is the order matters, right? In theory, you could create many DRM compositions and then issue them in any order you want. And this order matters for squashing purposes. I'll get to it in a couple slides, but one of the optimizations we do is for bits of the screen that haven't changed in a long time, we squash them all into one sort of intermediary buffer, frame buffer, and this saves us some composite time later on. But the order matters because we are using heuristic, essentially. This part hasn't changed in a while, which means we need to know the order of frames happening. So we don't do any planning until queue composition happens, and queue kind of locks in the order for what gets displayed onto the screen. Yeah, so that is part of the reading and writing a squash state right here. We call the platform version planes. This is where a lot of hardware-specific restrictions come into play, like Sean mentioned about, or have you mentioned that? Yeah, well, like there's restrictions with like rotation of YEV planes can only happen on primary planes on the Tegra or on the Pixel C hardware. It's, you know, silly things like that that we didn't want included into our nice clean abstraction. And that will take all of the layers for the display, try to put them in the planes. There'll of course be leftovers. If you're given 9 planes but only 3 hardware overlays, you're gonna have to do something with that. And that is where separate layers comes in. Its job is essentially to process the layers into a form that the compositor can actually use. If you think it's sort of simple how it happens, how we get input from Service Slinger. You know, we get a bunch of layers. They are positioned in the screen. They have a specific source buffer. You know, the naive implementation would be to just, like if you were doing a GL compositor for this, would be to just, you know, render your layer here with the texture, and then render the layers on top of that with the appropriate blending and alpha, and then it just sort of works. But that's not what we do. We actually separate the screen into non-overlapping rectangles, and that's what the separate layers does. And it basically chooses rectangles in the screen. I actually have a picture for it that I think can help explain what I'm talking about. A little ahead of ourselves here, but it does this. Essentially, it tries to separate the screen into discrete components that have a solid layer deck. It converts into this data structure right here, which is a rectangle, and that rectangle has source layers. It doesn't say where those are cropped from. It just has a composition of layers. For example, like 6 here, probably the most complicated, right? It's made of a dialog box and the app's little window behind it. I couldn't figure out how to do transparency properly, but let's just say this would be like a transparent dialog. Maybe there's a bit of shadow on the outside, and that gets composited over the layer behind it. And this ended up being a good optimization for us that I'll get to later. How do I go back? I'm running short of time, aren't I? Yep. Okay, so then it assigns fences in order of completion. This is just because of how timeline fences work with Android. You have to issue them in order, and only at this point do you actually know the order to release them. And then for each display, we queue the composition. It's just a standard implementation of a queue that we have, and then we work on to the next thread. Which, remember those threads he mentioned before? All those threads, the compositor worker and the frame worker, explaining them here in composite and framework routine. So composite really takes that plan we did in phase 1, because HWC had already returned at that point. Service Slinger has regained control of the main thread and is now doing its own business, but we still have to display our frame. We create a geocompositor, pop off the next one, prepare the frame. That's basically our word for apply the plan that we've been making, that we had just made. It's at this point that we squash regions. Remember those regions in the picture I mentioned here? Each one of those numbered areas is a region, and we have the capability to squash them. A very common case for this kind of thing is like only box 9 will change because like the time updated. Nothing else changed. The user is just kind of sitting there. At that point, it's a waste to composite the dialog box onto the app, onto the status bar, onto the navigation bar, because that's just going to be a lot of memory bandwidth that isn't really doing anything useful when we know that only area 9 will have changed, because it's the only one whose buffer has changed, and the geometry of the scene itself hasn't changed either. One of the nice things Service Finger gives us is a bit if the geometry changed. So that squashing, happens as part of the composition step, and then of course we composite all the other stuff that we couldn't fit into layers. And then at that point the frame is ready for display, and the composite thread needs to start compositing other stuff. It can't be bothered to wait for the next page flip. Frame routine routine actually handles that part, waits for everything to be ready to render. It waits for page flip, does all the atomic commit stuff, big long list of properties there. But that's your, I think you guys have a good idea of the DRM stuff behind that, standard. And then it works. Or if it doesn't, we blank the display. It has special logic for that up there too. Was there one more thing you mentioned for that? Oh, that's right. Yeah, because we have to free the resources. There's a lot of details that I omitted here because, not for hardware-specific reasons, but because interfacing with Service Finger is a bit strange sometimes, and you really have to be consistent about freeing things on time and when you're not using them. So we have logic for that. Is this one of your slides, I think? Or am I doing this one? Oh, this one. Yeah, so that's just to show you again. I know that was a whole lot to sort of think about all at once, especially in such a high level, but I was just trying to give you something to look at that'll help you kind of guide yourself through the code. Again, this is a high level how it works. Service Finger just gives us layers. We separate the layers into separate compositions for each display. It then does a planning phase right around here-ish, and by the time it does a jump to the next thread, it's already done planning. Compositor worker just kind of executes that plan, does the composition and swashing, and then sends it on to the frame worker, which just does the DRM stuff that we need, standard DRM stuff to display things. So yeah, I'll quickly talk about the separate rectangles algorithm that I use here. There's probably an algorithm like it that exists, but I couldn't really find it. But it was pretty simple to make up something, which essentially is like a sweep line algorithm. What Service Finger gives us is like windows, standard rectangles, and my goal was to essentially turn it into non-overlapping rectangles with homogeneous composition. Essentially, region 3 is always made out of the same layers, no matter what pixel you're on. Like if you're looking at like a different view of it, like if you're looking at this rectangle right here with the whole big blue area, not every pixel in the blue area on your screen is going to be made of the same stack of layers, right? Some of it's just going to be the app, the blue pixels. Some of it's going to be some blue pixels and some dialog pixels. Like up here, it's going to be some app pixels and some status bar pixels. So that's not what we want, because in the compositor, what we actually end up doing is we take one whole region, one of those pink numbered regions, and stick it into one draw call. And we actually do blending in the shader. This is kind of similar to how I'm told some tiled renderers end up doing blending with GL, is they collect all of the draw calls in one area, and then they don't output to a frame buffer and then read back to it just to complete the blending operation. It does it all at once in one sort of invocation, and we kind of do that manually in our GL compositor. So we generate like something like 64 different shaders or whatever maximum layer stack we think will ever exist. And for some examples here, for 2, for example, it's just going to be app pixels. We use the simplest shader of just one layer. It extracts only one texture, doesn't do any blending. Outputs directly to the frame buffer. Something a bit more complicated, maybe like layer 6 here. It'll take 2 layers for the dialog box and the pixels under and the app layer. Composite those all in the same kind of for loop inside that GLSL shader. And this, of course, helps with memory bandwidth, because we're not outputting to a frame buffer and then doing blend operations where it has to read back from that frame buffer and write back to it again. And we don't need to allocate more frame buffers as well. So that was kind of covering the first optimization. We don't do any blending. We don't do any GL blending, I should say. We do it all in the shader. Currently, if you look at the code now, we have kind of one hack specific to our pixel-C, which is we have a thing to import buffer handles directly into EGL images. I think there's a fix for that now. I just haven't implemented it, but that's kind of one of those things you'll see now. And you might have to contact your driver developer to give you that sort of a similar kind of extension, import a buffer handle into an EGL image. But for frame buffers where we actually have the Android graphic buffer, it's much easier and more standard. Just use the Android image native buffer. Another thing we do is cache frame buffers, which I would talk about, but I'm running out of time. It isn't super important. I'm going to talk about the planner. Sorry, I'm giving you much time.
Yeah, that's okay. So the planner, like I said, was introduced with Android N, and basically it's a way for you to plug in different quote-unquote plan stages, which is just a fancy way to say that it maps a surface flinger layer to an overlay. And so an example of a plan stage would be take the topmost surface flinger layer and assign it to any available overlay plane, and then repeat that until we fill up all of our overlay planes. And then maybe the second plan stage would be take all of the rest of the surface flinger layers, squash them down into one frame buffer, and then put it on the primary plane. So that's essentially what we do for generic DRM hardware composer that you would be running on just an arbitrary platform, is just use up all of the overlay planes, and then for the primary plane just put all of the rest on it. The reason we added the planner was to, like Zach said, work around some of the limitations in NVIDIA's hardware, and I think we could probably use it for things like if you, say, had a layer that had to span 2 hardware overlays, then you could, add a plan stage that basically mapped 2 overlays to the one. So it gives us a little bit of flexibility. And so, okay, so now this picture again, you're thinking like, what the hell did you guys build? Oh my God! And you're right in thinking that, because it's kind of convoluted. And a lot of this stuff actually just works around the lack of fence support in the kernel, which Gustavo has added recently. So for hwc2, which is the next version of the Hardware Composer API, it changes the expectations of when sync fences fire. And so that allows us to basically remove all of the threads and use an asynchronous atomic commit call right on the surface flinger thread. And so we can just like delete large swaths of code, which is awesome. And so hopefully this is sort of going to be the new world that we move to. And then finally, we are hosting DRM Hardware Composer on the Chromium Garrett Git tracker code review site thing. And we are happy to accept any external contributions, assuming you can sign the CLA license, which is, I think, pretty standard thing for committing to Chromium and Android. I think we've only had one external contribution so far, so thanks to Rob Herring for that. And this link will give you all of the details about how to get the source and submit patches. So I think that's it for us.
5 minutes for questions,
yeah,
I think?
we have time for questions? Yeah.
Yeah, that's right. Yeah, so he was asking, I'm sorry if I can interpret that right. So if blending happens in the shader, how does it get the fragment from the frame buffer? And so to answer that question, so it doesn't ever read from the frame buffer it's writing to or any other frame buffer it's made. It takes it from the input source layers, essentially. The stack of layers that Service-Linger gave us, we import directly as an EGL image and then as a GL texture, and then we do texture lookups from that and then composite directly to our target frame buffer.
Does that mean then, since you're doing the blending in the shader by doing repeated texture lookup of all the layers at a point P, does that mean then you have a limited number of layers because you have a limited number of textures to read from?
Yeah, that's correct.
And also, if you have more layers, you then launch a different. If you have fewer layers, do you then use a different shader?
Yeah, that's correct. We have a shader for each layer depth. I think it goes on PixelC up to 32 before it uses to compile any more shaders. We haven't run into that limitation of a layer depth being too big.
Okay, but the thing is that every layer is a separate texture then.
Yeah, that's right.
So you're limited by how many texture units the GL implementation underneath supports.
Yeah.
And I think the minimum value is supposed to be like, the minimum maximum value is like 16, I thought.
So 16 is more than enough. I don't think I've ever seen anything deeper than 5, maybe 6, 7, 8. They just don't get that complex in the Android world. If you actually look at the source code now, there's like a to-do fall back to actual blending if we run out. So that's like a real problem in theory, I guess. It should be fixed, right? There should be a fallback. We just haven't run into that yet.
But it probably won't be on a mobile platform because you don't have 12 windows open. But the thing is that the main purpose of this is you want to just launch fewer fragments on your fragment shader. Is that right? What this optimization is doing, because blending if you have a fixed function blending unit, which is not on a lot of tile-based renderers, but is on most immediate-based renderers, you get better power efficiency because it's fixed function. Rather than doing the multiply and adds in the shader, if the fixed function does it, you get better power efficiency. And the read from the render target is also cached because you have a render cache in most GPUs as well.
Yeah.
So I don't understand how this actually optimizes things for anything off besides maybe tile-based renderers.
I mean, I guess I see what you're saying, and the hard part with that is that it does depend on the hardware. And so I could see under some workloads this not being an optimization, or some target platforms it not being an optimization.
Yeah, target platform. It's kind of workload independent, but target platform dependent.
Yeah.
So like Kevin, you have to keep it short because there are other questions.
Oh.
This is a discussion.
Yeah, it's a good discussion to have, definitely. So thank you for your question.
So, yep.
But do you use atomic check, or do you not use that?
Sean?
Because it wasn't there in your talk, so.
Yeah, no, we do use atomic check.
I totally elided it from my overview.
We use atomic check right before we queue the composition, I think. So
Okay.
we use it right in here before we do this. And so once we get to here, then it should be checked.
Yeah, that's correct.
Yeah. We used to only do it when the composition changed, but then that got us in trouble, so we do it a lot more often now. But we do it. And then if it fails, right now we're kind of stupid about how we go about things if it fails. So if it fails, then we just lose our minds and squash everything and put it on the primary plane.
Okay, one last question. Well, very good. Thank you very much. Oh, wait, there is one.
Oh.
Hi, it's a very nice presentation. How you guys allocate buffer? You use a Gralog or TMA buffer, and Android will use GBM or Android specific.
For the frame buffers we use in hwcomposer, we allocate them using the graphic buffer C++ class that comes with Android, which under the covers will use Gralog.
Inside under the hood, it's a Gralog, right?
Yeah, under the hood we allocate our buffers using Gralog. It comes down to Gralog, which I guess can come down to anything else.
Android won't use GBM in the future.
I'm sorry, I didn't
GBM. The nowadays Chrome OS and many Wayland use GBM.
Oh, right.
To create EGL context.
Yeah, we have been thinking about how to get that working, but I don't think that's a solved problem, or we really have a clear plan on how that's going to work yet. But yeah, I think we want to use GBM.
Well, we can't. In hwcomposer, we still have to use Gralog because Gralog is sort of embedded into the Android world and how it works. Whatever Gralog is implemented with, it doesn't matter so much to DRM hwcomposer, as I understand it.
Right. Yeah, we were talking about Rob Clark and I were talking about sort of putting GBM or a few GBMs underneath Gralog and doing it that way, but I think we're still sort of trying to hash that out.
I think I've been seeing some promising stuff.
Okay, we'll have to cut it short, sorry. Thank you very
Okay.
much.
Thank you.
Yeah, 008734. So tell me if I need to repeat. So yeah, small W, no caps, 008734. For the password, this is capital C A42 dash, I should make it bigger. Then it's a small h, then 66. Okay? Which AP? It's Hagaelia Public. Okay. Is it working for everyone? Okay, very good.
Does it work?
Yeah. So we still have 10 minutes, 5 minutes. Anyone interested in helping with the mic passing and stuff like this? Okay, well then get closer to the front. And on this side, do you want to do it? Okay. The people without tags, well, I mean, there should be tags somewhere in the audience, otherwise there are some here. So just come and write your name and your, first name, last name, and company name.
Hello, my name is Gwangyeong and I'm working for Samsung Tizen team. Actually, I'm Tizen Windows System team. Today I talk to Tizen 3 Windows System integration layer of OpenGLES, EGL, and Vulkan driver. Actually, we call it libtpl-egl and vulkan-wsi-tizen. It's package name and we use it tizen.org repository. Today, first I show the brief of Tizen 3 Windows System architecture, and next Tizen 3 Windows System integration layer of OpenGLES EGL. Lastly, Tizen 3 vulkan-wsi for Tizen. First, Tizen 3 Windows System architecture. Currently, Tizen 3 uses the Wayland Windows system, and we poked the E12. Enlightenment and enlightenment as Wayland display server. And we use TDM display manager and TBM buffer manager and the libtpl-egl and vulkan-wsi-tizen. TPL-EGL is an abstraction layer for surface and buffer management on Tizen platform aimed to implement the EGL layer of OpenGLES driver over various display protocols, because Tizen uses the Wayland EGL and GBM and TBM. And TBM is off-screen we use TBM as off-screen rendering, like as GBM. And vulkan-wsi-tizen labs the vendor Vulkan ICD and provides the WSI for the Tizen Windows system. Tizen Buffer Manager provides the abstraction interfaces for the graphic buffer management manager in Tizen. Tizen Display Manager provide the abstraction interfaces for the display server, such as a Wayland server, to allow the direct access to graphics hardware in a safe, efficient manner as a display hall. Actually, Tizen uses the DRM, but most of SoC vendors fully support the DRM, so we define smaller DRM version split to Buffer Manager and Display Manager. Buffer Manager is TBM and Display Manager is TDM. TDM works as TDM set mode setting and page flip stuff. Today we focused on libtpl-egl and vulkan-wsi-tizen. And Tizen provide the core GL. Core GL is the lab of GL driver. Most of GL applications knows as core GL is a real driver, but core GL labs the vendor driver while loading DL often. They do support FastPass. It is software make current and EGL OpenGLES debugging and performance logging for Tizen. Next, libtpl-egl. Tizen, it is Tizen porting layer for EGL. This diagram shows the Tizen OpenGLES and EGL architecture. Tizen Windows system. libtpl-egl front end. libtpl is consists of libtpl-egl front end, back end. libtpl support TBM backend, Wayland EGL backend, and GBM backend currently. So GPU vendor driver don't handle Windows system protocols. TPL provides the implementation of EGL platform functions on Tizen platform. This diagram is the brief of Tizen porting layer architecture. Tizen has various Windows system protocols Wayland, GBM, and TBM. Before Tizen 2.4 support X11 and Tizen 3 Alpha also support X11, but we retired it. And we need to separate the common layer, front end, and duplicate code and backend for maintaining. So we make TPL-EGL API prevent burdens of easier porting on various Windows systems. VenderGL driver Windows system porting layer functions with only TPL-EGL. So if libtpl has improved performance, then vendor driver can get it without any modification of code. Vendor driver just use their driver with TPL front-end interface. Tizen porting layer of core object provides these three objects: TPL object, TPL display, and TPL surface. A TPL object is base class for all TPL objects. And TPL display encapsulates native display object like double display, GBM device, and TBM bulb manager. TPL surface encapsulates native drawer object like double surface, GBM surface, and TBM surface queue. Yes. TPL provides TPL object with corresponding to EGL objects. Top gray box means GL driver object, and intermediate box means TPL object, TBM surface. Bottom boxes means Windows system DRM objects. TPL display corresponds EGL display or native display. And TPL surface corresponds EGL surface or native drawer. TPL-EGL uses the native buffer as TBM surface. TBM surface has internal BO, and the internal BO includes the DMA buffer. So EGL driver can get DMA buffer from TBM surface. This diagram shows the GLES drawing API flow. Application usually use this flow, and vendor driver should implement corresponding these APIs. First, when EGL initialize is called, vendor driver should create drivers display. They just call TPL display create, and next, when EGL create Windows surface is called, vendor driver should create their Windows surface. At that point of time, they can call TPL surface create. When the driver want to get the target buffer, they can call TPL surface DQ buffer. TPL surface DQ buffer returns the TBM surface. The driver can get DMA buffer from TBM surface. And then, lastly, application calls EGL swap buffer. Driver should post the target buffer. At the point in time, they can call TPL surface enqueue buffer. TPL surface enqueue buffer internally call Windows system post to Windows system protocols. This is a simple example of the Tizen porting layer. Vendor drive just call like this. First, TPL display create and TPL surface create. Then they want to buffer. They just call TPL surface DQ buffer and draw something to the buffer. And then lastly, they call TPL surface enqueue buffer with the buffer. In the GPU vendor driver, the draw something part is what the GPU frame builder does. TPL-egl exposes the native buffer. As I mentioned, native buffer as TBM surface. If TBM backend uses DRM backend, GL drive can get DMA buffer from TBM surface, the buffer object. Follow slide shows the TPL front-end API. TPL object is base class for all TPL objects. It provides common functionalities of all TPL objects. TPL object is maintained by reference counter, so there are reference count APIs. TPL display encapsulates native display object, Wayland display GBM device TBM buffer manager. Any other objects are created from TPL display. They are in a backend type from TPL display. TPL surface encapsulate the native drop object, double surface, GBM surface, TBM surface Q. Its main features are to get the buffer for a surface and to post the buffer to a surface screen. This diagram shows the Wayland server and the client on TPL-egl. Wayland display server uses the TBM GBM backend, and Wayland-egl client uses the Wayland-egl backend. There are two arrows to access enlightenment to connect to Wayland TBM and libtpl-egl connect to Wayland TBM. Tizen uses the Wayland TBM instead of Wayland DRM because we expose the buffer accessing protocols, so enlightenment server can get the buffer directly, and other component can get the buffer directly, like multimedia frameworks. Enlightenment directly connect to Wayland TBM case means it is no compositing mode like Android's hardware compositor, and server's libtpl-egl connect to Wayland TBM case means composite mode. So no composite mode, they just get the client buffer and page flip to screen. This is buffer flow between Wayland server and GLES EGL driver. Actually, libtpl uses the TBM surface queue buffer flow, and libtpl-egl left that buffer management. When renderer want to their buffer, they just can TPL surface DQ buffer, and the rendering is done. They just call TPL surface enq buffer, and presenter in here enlightenment want to page flip something, they can call TBM surface Q acquire, and then the page flip is done. They just call TBM surface Q release. Actually, current enlightenment uses the GVM backend, so that is encapsulated by GVM backend, Tizen's GVM backend. We are shifting to GVM. We are shifting to GVM to TVM. So this diagram just called TVM APIs directory. Lastly, I introduce you vulkan-wsi for Tizen. This diagram shows the Tizen vulkan architecture, simple Tizen vulkan architecture. We use Kronos vulkan loader and vulkan loader loads vulkan-wsi Tizen. And vulkan-wsi Tizen loads vendors vulkan ICD. vulkan-wsi Tizen uses the libtpl-egl for communicating Windows system. We make the vulkan-wsi for Tizen for these objectives. Applications should be able to use Kronos vulkan loader and do not modify Kronos vulkan loader and separate the WSI binary across multiple vendor ICDs. And don't do any platform specific things. Use just the use TPL. Just use TPL. So we make the vulkan architecture like this. vulkan-wsi Tizen left the ICD and acts like a complete ICD. Yeah, Kronos vulkan loader exposes vulkan symbols to applications. Load open an ICD shared object file and dispatches ICD functions via hwcomposer get instance prog ADDR. This is recommended the way the Kronos loader document. Application calls the loader function, then loader function finally calls the dispatched ICD function. Foo bar and bars means the I use foo bar and bars used for VK APIs because VK API is too long. vulkan-wsi Tizen acts like a complete ICD. It exposes the VK ICD get instance prog ADDR, which it dispatches all required vulkan functions. Some functions are implemented in vulkan-wsi Tizen, and while others come from vendor ICD. vulkan-wsi Tizen hooks desired vulkan functions. Hooked vulkan-wsi Tizen functions are dispatched instead of ICD functions. So VK get instance prog ADDR and VK get device prog ADDR hooked by default, because if not, on vendor ICD functions might be dispatched even though it is hooked by vulkan-wsi Tizen. vulkan-wsi Tizen merges the extension from vendor ICD and the vulkan-wsi Tizen's own extension. vulkan-wsi Tizen hooks extension enumerate functions. There are two enumerate functions: VK enumerate instance extension properties and VK enumerate device extension properties. Tizen 3 uses the Wayland window system, so VK enumerate instance properties merges the vendor ICD instance extension and VK KHL Wayland service. Some vulkan-wsi functions are provided the Chronos loader. Surface functions are implemented in Chronos loader. Surface object is passed to the vulkan-wsi when the other wsi function is called, like vk create swap chain kchar. It is implemented in vulkan-wsi-tizen. WSI functions. Vulkan-wsi functions except surface functions are implemented and hooked. There are three WSI function categories: surface capability, query function, and swap chain function, and display functions. Actually, the current Tizen 3 does not support display functions yet. Swap chain related APIs. It is implemented in vulkan-wsi-tizen. Swap chain manages the image buffer queue. We can acquire next image buffer. We can acquire next image kchar, acquires our next code for acquiring our next image from the presentation engine. This presentation engine means in Tizen, enlightenment, and the libtpl-egl. VKQ present kchar used for present the given image to present engine. All of things implemented using TPL surface. VKQ next image kchar uses TPL surface DQ buffer, and VKQ present kchar uses TPL surface enq buffer. In Tizen, VK images corresponding to TBM surface. In Tizen, vulkan-wsi-tizen request these three extensions for implementing Tizen's vulkan infrastructure. Vendors ICs should these functions are defined in vk-tizen.ac. Vulkan-wsi should be able to dispatch those functions via vendors vendor ICD's vk ICD get insert proc ADDR. First, vk create image from native buffer Tizen. It creates a vk image from a Tizen native buffer. In here we use TBM surface. It is called by vk create swap chain kchar of vulkan-wsi-tizen. It returns vk images. Vendor ICD should create vk image from TBM surface. VK acquire next image kchar uses this VK image. Next, VKQ signal reads image Tizen. When the vendor's vulkan driver ends up the handling of VK image and it is ready to present, vendor ICD notified to vulkan-wsi-tizen. It is called by VKQ present kchar of vulkan-wsi-tizen. It returns native fence FD. Vendor ICD should create native fence FD from weight semaphore list. Vulkan-wsi-tizen weights native fence FD by TBM sync fence weight. Actually, TBM sync features are implemented by Android sync. Lastly, VK acquire image Tizen. it notifies the occurred image which is led to use to vendor's vulkan driver. It is called by VK occur next image capture of vulkan-wsi-tizen. There are native fence FD for input. Vulkan driver should wait this native fence FD until display server triggering it. Native fence FD is created by TVM sync fence create. Display server uses TVM sync fence timeline increase for triggering. Currently, vulkan-wsi implements most of surface and swap chain functions, but present mode and display functions are not implemented yet. Or actually, VK present mode mailbox capture is only implemented. There are introduced the project Git repository. libtpl-egl reference. There are libtpl-egl reference driver in Tizen repository. The emulator YAGL is emulator driver of Tizen. Before emulator YAGL implemented by DRM. So, and then we implemented it with ported to libtpl-egl. So following commit explains how to port the driver with the libtpl-egl from the traditional DRM based the driver. Thank you. Does any questions? Yep.
So, do I understand correctly that the application sees the Wayland Vulkan extensions?
Yes. Actually, in Tizen, application directly use Wayland APIs because in Tizen, they use EFL library. EFL library labs Wayland APIs.
Okay, so how does that work with TPL abstracting or having other backends than Wayland?
If you are GPU vendor driver developer, you can reference emulator YAGL for how to use libtpl-egl, and I think you do not implement another TPL backend for Tizen because Tizen uses only TVM, GVM, and Wayland EGL backend. So if you want to port the libtpl to another operation OS, you can implement that Windows system.
Okay, but for Vulkan, it's basically Wayland only?
Excuse me?
For Vulkan, it's Wayland only?
Yes.
Okay, thanks.
Yeah.
So so Tizen is providing an ICD.
Yeah. Yeah.
So Tizen is providing a Vulkan ICD between the loader and the vendor ICD.
Yes.
So my question is, of course, the Tizen ICD is providing an implementation for some WSI functions.
Yes, only they provide WSI functions.
Okay. Does that ICD provide any additional functions, or is it only WSI?
Oh, they dispatches the vendor ICDs, the Vulkan APIs, and when the non-WSI API is called vulkan-wsi-tizen ICD calls pass to vendor ICD's APIs.
Right. And the Tizen ICD is providing WSI functions to the application.
Yes.
Does it also provide any additional functions, additional extensions?
Actually, currently, Tizen vulkan-wsi-tizen only provide WSI functions. Yeah.
Okay. Thank you.
Yeah. Yeah.
So, you have the Tizen ICD sitting underneath the Kronos loader ICD.
Yeah.
But would it also be possible to implement that as a Vulkan system layer on top of the ICD instead of below it?
You mean vendor want to implement their WSIs? They can do it.
I guess what I'm asking is, could the Tizen WSI layer be implemented as like a layer, rather than a separate mechanism between the Kronos loader and the vendor ICDs?
Yes.
So could it just be done using the basic layer mechanism of Vulkan itself, rather than having a separate thing in between the two?
We just remove the burden of the vendors implementing Tizen Windows system. So we just implemented WSI functions for vulkan-wsi-tizen. Yes.
Okay. So is it a Vulkan layer, or is it something different than that?
Excuse me?
Is it technically a Vulkan layer? Like
Vulkan layer?
Yeah.
No, actually, a Vulkan layer is implemented in Vulkan loader. So they has performance burden. So, and when manufacturer ship the product, they can remove the Vulkan layers. So we does not use the Vulkan layer for implementing WSIs. We work at we don't want to modify Kronos loader, so we implemented the real ICD.
Okay. I'm still not really following what the difference between doing that and using a layer is myself, but maybe I'm misunderstanding.
Is it, sorry to try to answer that, is it just because to do WSI stuff you would need surface extension or instance extensions, and those require modifying the IC or the loader to support the instance extension, and they didn't want to modify the loader?
Can you speak more loudly?
Yeah, so is the problem that to do it as a layer and as, well, no, I guess you've already got instance extensions to be able to do it. So how did you, I guess you've got the same problem. I was just wondering if it's because you've got to modify the loader to do instance extensions, which the WSI stuff would need, then you could fake it as an ICD perhaps. But
first, we don't want to modify the Vulkan Kronos loader, so we does not try to this implementation method. Yeah.
Okay. Thanks for the questions, and thanks for the talk. And thanks.
Yeah.
So next presenter now, David, Arc++.
Got 3 minutes.
And when do I need to end?
I'll tell you, but it's something like 40 minutes.
Okay.
Let's say at 20, you should, yeah, so you have half an hour to present.
Okay.
Questions included, and then probably go a bit over.
Right.
It's fine. Yeah, 30 minutes.
Should I wait for minutes or?
No.
Sorry?
To go, just don't unplug it until, well, basically all the questions are done. Simple enough.
Great. Okay. Hi. I'm David, and I have actually been to an XDC before. Some of you might recognize me. I used to work. I'm alive. For the last 5 years, I've been working for Google on Chrome and Chrome OS, mostly focusing on graphics and the compositor inside of Chrome. For the last 12 months, I've been working on a project called Arc++, and today I'm going to tell you a bit about it and explain some of the pieces that makes the graphic stack used for Arc++ work. And I'm going to go fairly quickly through the slides because I can't do an XDC talk without some demos, so I'll try to fit that in at the end. So what is Arc++? Arc++ is Android applications running on Chrome OS, and it's done by having Android run alongside Chrome OS on Chromebooks, and it provides the user with the full Play Store and all existing Play Store apps
on Chrome OS. A little bit of background. The name Arc++ comes from a previous product called Arc, which is short for App Runtime on Chrome. It was a previous attempt to bring Android apps to Chrome OS. It was done as a Chrome plugin, Pepper plugin, and each application would be isolated within that plugin, which was great. It fit in pretty well in the Chrome model, but it required developers most of the time to modify their applications for them to run within this environment. And it didn't, we had to emulate a lot of layers, and that added quite a bit of overhead. So it never really took off. Arc++ is another attempt at bringing Android apps to Chrome OS. It shares a lot of the goals for the original Arc. A few things are different. This time, we really want to bring the full Play Store without developers having to modify their apps. We wanted to minimize the changes we had to do to Android to make this work, just to make it easier to maintain. And we want to keep Chrome OS secure, just as before. That's very important. And we want to keep the Chrome OS update model. So that is, for those who don't know, we provide a update. Usually every 6 weeks you'll get a new fresh version of Chrome OS. This is an overview of how sort of the graphics works with Chrome OS. So Android, as I said, runs alongside Chrome OS. We're basically taking advantage of Linux containers for this. Android is isolated from Chrome OS as much as we can isolate it. We're using PID namespaces and all that goodness. Chrome OS runs just like before. It has the same privileges as before. So for rendering rendering for Android apps, most Android apps will use the hardware accelerated canvas API, and that's since Android 4 implemented on top of OpenGLES. So that your Play Store, for example, would just use this canvas API. A lot of other applications on games and Chrome on Android, for example, will use OpenGL directly. And in the future, a lot of applications will use Vulkan. Whatever API being used, the target of all drawing operations is a surface, which is backed by a buffer queue, and the buffer queue is consumed by Surface Slinger, and the buffers are allocated by Gralloc. For Arc++, Gralloc and the Julius driver is using DRM, Direct Rendering Manager. Apps still have access to fully accelerated GL driver. Performance is the same as if you would be running it if you would turn your Chromebook into just an Android device. The performance would be the same. Shouldn't be any penalty from what we're doing. And like I said, in the future, applications will use Vulkan, for example. It doesn't really matter to the Arc++ model. as long as they target one of these gralloc buffers, it will work. Traditionally on Android, you'd have applications producing surfaces that are consumed by Surface Flinger, and Surface Flinger will do compositing using ELES, with the option of actually offloading some of the compositing to hwcomposer and using hardware overlays. In the ARC++ case, what we do is we try to handle all surfaces as if they were possible to handle using hardware overlays. But really what we're doing is we're instead forwarding all the compositing over to the Chrome side, where it gets inserted into the compositor inside of Chrome and gets composited with the rest of the Chrome OS UI. And then the compositor on the Chrome side will instead look at the whole scene and all the combining the UI with the Android apps and determine whether you can actually use hardware overlays depending on the device and so on. Window management. This takes advantage of some of the work that's been done lately on Android and multi-window support. But some of the window management is shared. It's not what you typically expect. It's some operations are being handled by Android and some are being handled by Chrome. This might change in the future, but as of today, we're handling some state changes on the Chrome side, and Android still gets the ability to do a few different things like absolute positioning and resizing. But it still provides a very good integration experience when you're using the applications on your Chromebook. So DRM and KMS are used on Chrome OS, and that's really how we're able to efficiently integrate Android and Chrome OS. We use the mechanism that exists for DRM to share buffers across processes. So we use prime file descriptors for sharing between Android and Chrome OS. It's worth mentioning that Chrome is your main compositor. Chrome acts as the DRM master, and it actually programs the display controller, while the Android side will not do any of that, and it doesn't have access to any of that, which means we can limit some of the access for Android, which is good for security purposes. Yeah, I mentioned gralloc. Gralloc is a mechanism on Android to allocate graphics buffers. On ARC++, we provide an implementation of gralloc that's using DRM. Applications are allowed they can map gralloc buffers and write to them using the CPU if they like, or they can use them as OpenGL textures. Right, and the gralloc buffers, as I mentioned before, we can get a DRM prime file descriptor for them and share them. On the Chrome OS side, Chrome is supported on a number of platforms, and we have abstractions for that. There's one for Mac, there's one for Windows, there's one for Linux. We have one platform called Ozone, and that's what's being used on Chrome OS. And then Ozone itself is actually has a number of different implementations. On Chrome OS devices, we use the Freon graphics stack, which is essentially Ozone implemented on top of DRM. And then if you take a step back into the Chromium code, we have a framework called the EPU memory buffer framework, and that allows all the code that we have in Chrome that is platform independent to take advantage of some of these low-level primitives that DRM provides, or if you move to a different platform, it might be a different type of primitive. On Mac OS, for example, we are able to make use of IO surfaces, which would be your DRM buffer equivalent. What we had to do for Arc++ was really just to extend this framework so that we could import a buffer that comes from outside of Chrome. And once that was done, then most of the platform-independent code in Chromium already knew how to deal with these buffers, how to composite them efficiently, and how to share them between processes within Chromium. The number of different pixel formats we supported in Chrome were limited. Android allows applications to use a few more, so we had to add support for those. Today, I think we support most of the ones being used by Android apps. And that means that in hwcomposer, when we receive a buffer, we can forward it to Chrome. If we don't have support for the format in Chrome, we couldn't do that, and we had to do some form of software fallback or convert it to the right format on that side before we could import it. These days, I think it's very rare that we hit that type of fallback. Our hardware overlay support in Chrome is very limited today, but that's something that we're working on. Our main use case today is when we realize that we have some application that basically covers the whole screen, and we can, there's no point in compositing that to one buffer of the exact same size and exact same format. Then we'll just take the application buffer and use that for scan out directly. But this is an area where we're probably going to see some improvements soon. There's a component for Chrome was created to bridge Android with all the internal components within Chrome for doing compositing and managing buffers. The name of this component is called Exosphere. It lives in the Chromium source code tree, and unlike the rest of Chrome, we at least within the browser process, that is trusted code. In this case, we don't really fully trust the Android side, so this provides some validation of all the commands coming in, and it provides the needed synchronization for how to handle these buffers. And it was built on top of the EPU memory buffer framework that I talked about before. Yeah, some of the window management is shared, so you'll see that you can still use the key bindings in Chrome to make windows maximized and so on. However, some things are managed on the Android side. The Chrome compositor, in Chromium Chromium is a multi-process architecture. You'll have one browser process that will start a new process called a render process for each tab you open. Each one of those render processors are sandboxed, and eventually what they do is they produce a frame that gets sent back to the browser process. So you'll have a compositor that sort of deals with the page, a compositor instance that deals with the page, produces a frame. It doesn't actually do any compositing. It will just forward the frame as a set of quads for the compositing needs to be done. So it gets delegated to the main compositor in the browser process, and that one will produce one frame for all the tabs. It uses textures typically for all these quads. The textures can be backed by EPM buffers, and in the case of R++, we also produce the same kind of frames with textures backed by EPM buffers that are have been imported from gralloc buffers. There's one difference in Chrome. Synchronization is relatively simple because we have one process that will talk to the driver. It's the EP process, and we have one single thread where we do that. So all we need to do from a synchronization perspective is make sure that the order in which we execute commands on that thread is as we'd want it to be. So we can just use some form of sync point that control the ordering happening on that thread. In the case of R++, all the rendering commands are no longer happening on that same single thread in the EP process, but in a separate process inside of the Android container. So that makes synchronization a little bit harder. For example, we can't start queuing more drawing commands until we actually know that the compositor on the Chrome side is finished with the buffer. This is another area where we're hoping to improve soon by adding support for the same type of synchronization that we have on Android today. It's called like explicit synchronization. R++ today is not using this, so we have to do this little fence dance to make sure that we're not drawing to a buffer that on the Android side that's currently in use by Chrome. For the communication between Chrome and Android, we decided that instead of coming up with a new protocol, we decided to use Wayland. So Wayland is used for anything graphics, window management, and input related in R++. There was a number of benefits with that. You know, it's a limited API, so from a security point of view, it's easier to validate. It was easy to add additional interfaces for what we needed that was not already part of an interface. A lot of the communication we needed to do between Android and Chrome, there was already Wayland interfaces for that. So most of it was already covered, which is a big benefit. And it was well tested, and we had a good set of existing clients out there that we could use to validate what we were implementing. And this allowed us to parallelize a lot of the work, and some could focus on the Chrome side and make sure that we implemented the Wayland interfaces properly as we at the same time worked on the Android side, and later we could connect the two. And in the future, if we might want to extend this type of external client to something beyond Android, then having implemented all these Wayland interfaces is a great place to be. Here, these are some of the interfaces that we use today, in addition to the core Wayland interfaces. We've added a few. We're currently kind of going through the process of figuring out which ones might make sense upstream, which ones should maybe be removed in favor of an alternative that's already upstream. Some of them exist because maybe the upstream one didn't perfectly fit our needs, and it was a little bit too much work to work our way around and making that work in the time frame we had. These can all be found in the Chromium tree, and I'll provide some links to them later. And we're interested in adding more interfaces in the future. I think the two main areas are what we need for explicit synchronization. That's for handling, releasing buffers and presentation timing, and then also support for protected buffers. Yeah, like I said, all the Chromium side code can be found in the Chromium source tree. You can just follow the general Chromium developer instructions to download all the source. These are the locations where you can find some of the things I talked about. All the bindings between Wayland and Chrome components can be found in the XO directory. The Wayland specific part of that in XO Wayland, and the third-party Wayland protocols have obviously the upstream Wayland protocols code in addition to the interfaces that we had to add for ARC++. So yeah, you can pull that down and use these arguments when building it, and you will have a version of Chrome that is also a Wayland compositor, supporting all the interfaces that I mentioned. So, how am I doing on time? Maybe I can do demos, a few quick demos, just showing how it works, and then we'll do questions. Does that sound good? So this is just your standard Chrome OS desktop. You can see one difference here. There's a Play Store icon down here. Otherwise, it looks like your normal Chrome OS desktop. If I click that, it actually pulls up the Play Store. I have noticed that the screen mirroring makes things a little bit slower. And if you want to see it at full speed, you can just grab me afterwards and I'll show you that, but it should still work pretty well. So yeah, you can just go through the apps and it's just a matter of installing them. And we'll see. There you go. And you can even see that some of these, notifications work. So it integrates properly with the notifications from the Android side. And as you saw, the app shows up here. I can't launch that, but I don't know if I have a... Okay, I shouldn't have launched that. All right, let's get rid of that one and start something I know works. Play music. You have that works as expected. And you know, an important thing is you could actually start multiple applications, and you can easily switch between them as you'd expect. And yeah. That should, let's see if I have anything else here. I can tell that Time Warner in New York City sucks, and I'm not online. And yeah, and I don't know what happened with Spotify, but that should work just fine. But yeah, all your apps should work. Games should run at pretty good speed. Let's see if this one. Yeah, it does run quite a bit slower because of the screen mirroring, but you get the idea. Yeah, gamepad support. We also have gamepad support, so you can plug in a gamepad, and that will work. I can do, if I plug in this machine is not in developer mode. So if you put your Chrome in dev mode, and then you can actually normal Linux apps. If you know what Crouton is, you can use Crouton. You could actually run your normal Okay. Now, questions.
For the drivers running in the Android side, is that a separate driver stack for the OpenGL drivers than the Chrome OS side, I would assume?
The drivers are almost the same on that. They might not be exactly the same version, but essentially, it's on top of DRM, so it's very much the same driver.
Okay, so there's no special modifications needed to support like this Android stack versus another Android stack versus a Chrome OS stack for the OpenGL driver, or do you need to do different?
No.
Okay.
I have two questions, but first a quick comment. about the question about driver differences. At least on the Intel Chromebooks, the Mesa running inside the Android container versus the Mesa running outside, there's a very small difference, and the only difference is there's some bug fixes to the Android one, and there's a few patches to better integrate with Android, but we're going to upstream all those. So the goal is to have the exact same version of Mesa built for the inside and outside the container, the same Git SHA. But we're not there yet, but it shouldn't be hard to get there. It's just a matter of review. You don't need any special hacks in your driver. Question 1. You mentioned you would like better synchronization. And on one of the slides I saw you were using ARB fence to do synchronization within the compositor. Android container all the way up to the Chrome compositor.
Yeah, that's ideally what we want to do. I think to get there, we probably need help from a lot of people in this room, and I'm excited to discuss everything that's needed, and what kind of time frame we might be able to come up with.
Maybe we should have a hack session while we have some downtime.
Yeah, that'd be great.
Question 2. You mentioned Chrome expects additional Wayland protocol for apps running inside the Android container, but you just ran some upstream Weston demos. If upstream Linux apps don't support, I guess I'm not a Wayland expert, I don't know a lot about Wayland protocol, what's the consequence of upstream Linux apps not supporting those Chromium Wayland extensions?
None really. If you have a client that's using the core interfaces, and maybe some of these are listed here, then that will just work. If you want to take advantage of some of the additional functionality that was added for ARC++ for some reason, although I wouldn't necessarily recommend it, I think I would recommend looking at how we could maybe make a better upstream version of them. But if you want to take advantage of them or test them out as it is, then those are also available to you on through Chrome on a Chromebook, or if you just build it on your workstation. And it's the ones I listed here.
Thanks.
Hey, it's a great presentation, and the most interesting thing is in your demo you launch arbitrary Wayland client app. It means we can launch any Qt and GTK Wayland app. So can you expect the Google open any Wayland application top of Chrome OS? It means it's a generic desktop OS finally?
Yes, so we have one big Wayland application on Chrome OS today, that's Android. There's no plans to add any other clients as of today, and normally on your Chromebook when it's not in dev mode, Android would really be the only one who have access to that socket. But like I showed you, if you put it in dev mode, you can experiment with it, and you could potentially use the Chromium browser to experiment with Chromium as a compositor on your Linux workstation. But there's no plans as of today. But maybe in the future we'll be able to make use of it for something.
Okay, thank you very much. Yeah, but we don't really have time now. We have 4 minutes to move to the other one. So, yeah. Sorry.
Okay.
Sorry, Raul.
Thank you. Okay. All right. I guess this is the last talk before lunch, so I'll try to keep it short. So my name is Andy Ritger. I work at NVIDIA, and I'm going to give a brief update on GLVND, OpenGL vendor neutral dispatching. Sorry, let me get things cloned here. That'll work better. Losing. Okay, good. Yeah. So GLVND is a new ABI for OpenGL. Defining the interface between OpenGL applications, the OpenGL libraries that those applications can expect, and OpenGL implementations. Defines a set of Windows system libraries for GLX and EGL, defines client API libraries, OpenGL and OpenGLES. It allows multiple vendors to provide their OpenGL implementations and coexist on the file system, and it allows multiple vendors to coexist within the same process. So the set of vendor-neutral libraries provided by GLVND are libglx, libegl, libopengl, libraries for OpenGLES, and then backwards compatible libgl for compatibility with what we have today. Oh, I'm sorry. What's our screen resolution? Yeah. 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 We'll go back to this. Nope. Yeah. Yep. All right. In the interest of time, we'll just run windowed. Okay, so going through a block diagram of the different components, in the case of GLX and OpenGL, you'd have your application talking to both the GLVND provided libglx and libopenGL. From a control flow standpoint, the application would presumably first call a GLX entry point to do all its initial setup. That will cause GLVND to talk to the X server, talking to the GLX GLVND extension to GLX to correlate what X screen the application is talking about. You know, pretty much any GLX entry point should somehow imply the X screen that it's talking about, either explicitly as an argument or implicitly by an argument that's a GLX object that references an X screen. From once the GLVND libglx knows which X screen is being used and it finds the vendor for that X screen, it loads that vendor's libglx implementation. Then during GLX make current, libglx will call the vendor implementation to construct the dispatch table to be used by OpenGL. Then when the application calls OpenGL API entry points, that will jump through to the vendor's OpenGL implementation. Of course. Okay, and then the flow for EGL is very similar. The one hiccup there is that we don't have an X server necessarily to query for the correlation between EGL objects and a particular vendor. So there's a little bit of guesswork there, and we'll talk about that more in a few slides. But otherwise, the control flow is pretty much the same as for GLX. So in terms of API support, the vendor-neutral libraries provided by libgl export GLX 1.4 entry points and GLX get proc address. libegl provides EGL 1.5 entry points and EGL get proc address. The libopenGL provided by GLVND exports OpenGL 4.5 entry points. The GLES libraries provide appropriate entry points there. And then libgl to provide backwards compatibility for applications who today are used to talking to different vendors. libgls, that's just a dumping ground of all the entry points that we could find exported by anyone's libgl. And of course, vendors can advertise additional entry points and new API versions at runtime. This is just the list of symbols statically exported. The set of symbols exported by each of these shared libraries. So for platform support, what's currently implemented in GLVND, NVIDIA is currently using it on Linux x86, x86-64, and ARM v7. We're wrapping up our port for AArch64. PPC64LE is in progress. Other platforms shouldn't be much work. For CPU architectures, there's a little bit of online generated assembly that you need for managing dispatch stubs. For porting to other Unix platforms, that should be fairly straightforward. The dependencies there aren't too high, but the details of that could be worked out. So the status from NVIDIA's standpoint, we're currently using GLVND with our driver. At install time, if you use our installer, the user can choose whether or not to use GLVND or not. We've been staging it in over several release cycles to make sure we get adequate testing. So once you decide whether or not, or once the user decides whether or not to use GLVND, then the installer tries to decide whether to use the distro's provided GLVND, and if that exists, then we'll use that. Otherwise, we've taken a snapshot from top of tree of GLVND and bundled that with our driver, so that running on older distros that don't provide GLVND, that'll be our backwards compatibility story. And our 361 release series, which was earlier this year, or maybe late last year, we initially shipped our driver running with GLVND for OpenGL and GLX. That was enabled by disabled by default but gave people a place to start testing it. Once we worked out a bunch of interaction bugs, we enabled it by default in our 364 release series. Our 375 release series, which is coming up soon, will include support for EGL. Most likely that'll be disabled by default, so we can get a little bit more soak time. And then the release series after that will hopefully enable use of GLVND's EGL by default. The status in Mesa. So Mesa has a configure time support for GLVND. So far in top of tree has that support for OpenGL and GLX. EGL, there's a set of patches out in review right now, and there's a configure options to enable that. To talk briefly through the implementation of the different libraries. One of the workhorses within the GLVND implementation is libgl dispatch. Applications don't directly link against this. This is really an implementation detail of GLVND, but it handles all of the dispatching and managing of stubs and generation of the stubs. It's based on GL API from Mesa. It looks up function pointers and looks up the function pointer dispatch table from thread local storage. The set of entry points that I mentioned a few slides ago, the GLVND knows about at compile time. Those stubs will be generated upfront as part of the build, and then future entry points that vendors register dynamically at runtime, those get generated on the fly. libglx.so is new. That's a new component to the ecosystem added by GLVND. But one of the nice things about this is finally teasing apart libgl, whereas before libgl.so contained both GLX entry points and OpenGL entry points. GLVND separates this out. So libglx only provides GLX entry points. And it dispatches to vendor functions, to vendor implementations based mostly on the function arguments passed to GLX functions. Like I mentioned earlier, most GLX functions you can infer what X screen is being talked about, either because there's an X screen argument or there's an argument of some GLX object that implies an X screen. Handling dispatching of vendor runtime registered entry points gets a little bit trickier because dispatching is handled based on arguments rather than a function table in thread local storage. So for any GLX extension function that the vendor registers, the vendor must also provide a dispatch function, or a dispatch function that the GLVND implementation uses to decide which vendor to actually call for that function. So then I mentioned libgl, so we provide that for backwards compatibility. Really the goal is that applications shouldn't be aware of any of this change if they don't want to be. The implementation of libgl provided by GLVND is a wrapper over libglx and libgl dispatch. And like I already mentioned, it exports all the symbols that we can find in anyone's libgl. And if you find anything that's missing from that list, let us know. Let's see here. So the vendor selection, the GLX vendor selection in GLVND, like I mentioned in the block diagram near the beginning of the presentation, relies on a new GLX extension that lets the GLVND GLX library query or correlate a vendor with a particular X screen. This gets a little funny when you deal with local or remote X servers. For a local X server, things fall out naturally. For a remote X server, that X server may not have this extension. The server reported vendor may not make sense on the client machine where GLVND is running. So in all those sorts of cases, GLVND needs to have some fallback path. So it really, in this case, it needs to fall back to GLX indirect rendering, if that's enabled in the server. And right now, GLVND doesn't provide its own indirect rendering client-side library, so it relies on one of the vendor's GLX libraries. And right now, that's somewhat arbitrarily chosen by a symlink from GLX indirect to GLX, one of the vendors that's installed. And while we've tried to structure everything to keep it clean and have screen granularity, in practice we can't actually have multiple vendors coexisting with screen granularity until we address server-side GLVND. But everything's been designed client-side to support that if and when we implement the server-side piece. Excuse me for some water. Okay, so the GLVND libegl implementation is responsible, of course, for exporting all of the EGL entry points. It dispatches to the EGL, to the vendor EGL implementation, again based on EGL function arguments, similar to how it works for GLX. But unlike GLX, it's a little bit harder to infer which EGL vendor we should talk to. So the GLVND EGL implementation needs to load all of the EGL vendors that are present on the system. And this is needed for some of the EGL functions that enumerate devices with system scope rather than a particular EGL display. And it's also necessary so that we can ask each vendor, hey, do you recognize this native handle? And the model for registering EGL vendor implementations is somewhat modeled after the Vulkan ICD. So EGL vendor selection is mostly driven by EGL display. Most EGL functions take an EGL display as an argument, and once we've correlated an EGL display with a vendor, then things fall out naturally from there. The tricky part is making that initial correlation. So for EGL get platform display, given the combination of a platform and a VoidStar native display, we can call each EGL vendor in turn and ask them, do you recognize this? Until someone says yes, and then from that point forward, the returned EGL display is correlated with that vendor. For EGL get display, there's some more guesswork, and it's not. This part could use a little bit of improvement to improve the heuristics. So most EGL functions take an EGL display as an argument, and then again things fall out naturally. But not all EGL entry points do. So EGL client extensions, the ones that are independent of any particular EGL display, do require special handling in GLVND. So whereas most of what I've described shouldn't require a lot of changes going forward for GLVND, EGL client extensions is one area where as new EGL entry points are added that operate without an EGL display, those will need to be added to GLVND itself. But thankfully that class of entry points and extensions is fairly rare. EGL KHR debug required a little bit of special attention in GLVND as well. In that extension, whenever any vendor generates an EGL error, they're obligated to call a registered callback function. And there wasn't really a way to manage that within GLVND itself. And so really any vendor implementation plugging into the system needs to provide this extension. One of the nice things with GLVND is consistency of function pointers. So however you get to an OpenGL entry point, either by linking against one of the GLVND libraries and just calling the symbol through that, whether you go through getproc address, either EGL or GLX, or even using DLOpen and DLSym to get to the entry point. All of those mechanisms should give you the same result in the same actual function being called. And as a consequence of this, you can have GLX and EGL running in the same process. So in the process of bringing this up, it exposed several classes of application bugs. I've just mentioned a few of these here. We've ran into a variety of cases where OpenGL applications would call OpenGL entry points without ever having made current on that thread. Of course, that's an application bug. NVIDIA's OpenGL implementation prior to GLVND masked that, made that call a no-op. I'm not sure what Mesa did in that case, but from our customers' point of view, when they upgraded to a GLVND-enabled NVIDIA driver, they viewed that as a regression. So we needed to provide some workaround. So GLVND, on the first GLX entry point it sees, it plugs in a no-op dispatch table. That's similar to what the NVIDIA driver did prior to GLVND. Okay. Yeah. Okay. For people listening to this stream, it sounds like Mesa did something similar prior to GLVND. Thanks, Ian. Yeah. Okay. Let's see here. There was a building the dispatch table. The OpenGL dispatch table can be expensive, and initially GLVND was doing that on every make current, and that was painful at times. So we've not been able to optimize that entirely, but we defer regenerating dispatch tables until you're actually switching between vendor implementations. So hopefully that's less frequent, but still applications we encourage to not do make current more often than you need. And as I was putting these slides together, I initially thought, well, it's surprising we didn't see a lot more bugs from applications being confused by a different set of entry points being advertised. But of course, we're not seeing that yet because our libgl provided by GLVND provides everything that that libgl implementations provided before. So we're not hitting that class of problem yet. It's likely that as applications try to move from using libgl to using libopenGL, they will run into problems with that'll unmask potentially poor assumptions they were making, trying to make decisions based on entry points advertised. So hopefully that encourages applications to be more rigorous about checking extension strings instead. So next steps for GLVND. So it needs more testing with Mesa. I was talking to Adam Jackson before this talk, and it sounds like that testing is going pretty well. And when we get to questions, I'd like to hear what else from Mesa you'd like to see in GLVND before we could enable it by default. We should get the EGL implementation in GLVND shipping and used on both Mesa and NVIDIA. We should encourage other OpenGL vendors to port to GLVND. And my hope is that once Mesa adopts this and can enable it by default, then at that point distros can start packaging this and providing it. And then at some point in the future, perhaps we should look at server-side GLX, GLVND. Jason, is there a, sorry.
So I don't know if, I don't know if you can answer this question, but so we have it, mostly working in Mesa. NVIDIA's working on it. Have we been able to talk AMD into using this yet?
When I spoke to some people from AMD last year, they were interested, but there weren't any firm commitments. I can't say any more for AMD.
Yeah, I think we got some more talk to them. We talked to them more recently this year, I think, actually, as well, and they were asking some questions about how to do it, but I haven't heard if they actually finished it or not, unless someone here has an update.
Yeah. Okay. And you know, I guess, you know, if the state today is that each vendor implementation, you know, provides libgl and provides a conflicting set of libraries, I guess once we have at least 2 vendors using glvnd, then, you know, for vendors who aren't yet ported, they're no worse off than they are today if we switch over to using glvnd. Jason, I hope you don't disagree with that statement.
So one other question that I just had was, what are we doing about the stomping problem? So your installer comes along and wants to install in a system. How does it detect that what's currently installed on the system is libglvnd and a new enough one, and so that you can avoid stepping over it and voting it back to an older version or whatever?
Right. I think there's... I don't know the details of the installer check. There's a bunch of complicated stuff in the details of that. As much as possible, we don't. If there's a glvnd on the system, we don't want to touch. We want to leave it alone and just use it. So, and that's part of the philosophy of, you know, we hope glvnd doesn't need to rev very often. So, you know, so that we don't have to. What's that? I can think of plenty of clever ways to fix that. You know, I think the nicest thing will be if you know, if glvnd is a fairly stable thing, you know, maybe it needs to be updated, you know, for, you know, occasional bug fixes, EGL client extensions, those sorts of things. But I think in general, for all of that, you know, with at least with NVIDIA's driver and our installer, we would package a recent snapshot of glvnd and install that on the system when we don't find glvnd there. Otherwise, if there is a glvnd on the system, we'll just use that and not try to be clever about, well, is that new enough for what we need or anything like that. Yeah, I mean, the whole point of this is to avoid those sorts of file system conflicts. Okay. So it's here. So yeah, so call to action. Any other OpenGL vendors that are interested in this, you know, we encourage you to port to the glvnd infrastructure. It should be fairly straightforward to do. You need to provide a libglx vendor shared library and implement the interface defined in this libglx abi.h header file. There's something comparable for EGL. There's a handful of EGL extensions that we require vendors to implement to plug into this, and the patches to Mesa to port to glvnd should hopefully provide a good example of how to port to it. And for Linux distributors, you know, hopefully once Mesa's to the point where Mesa's comfortable with it and we can enable it default there, enable it by default there, then we would encourage distributors to start packaging and shipping this. And then if for distros who repackage the NVIDIA driver, use the glvnd enabled version of the libraries contained within the NVIDIA driver package. For OpenGL application developers, you know, please test out this new system, and either with the top of tree bits for Mesa or with NVIDIA, provide feedback, help us shake out any other bugs in the system. And my hope is that over time, as glvnd becomes commonplace in the ecosystem, that applications going forward will start using libopenGL and one of or both of libglx and libegl, and
we view libgl as deprecated. And just a reminder, only call OpenGL entry points from a thread when you have a current context. In glvnd, we added an environment variable that may be useful to. So far, the only thing it checks for is that case, but that seems like a useful place to a useful environment variable to use for other kinds of that sort of checking. Using that environment variable while you're doing development may be useful. So that's all I have. I forgot to mention at the beginning of the slide deck, I'm really just presenting the information. Kyle Brenneman at NVIDIA has done all the implementation work on this lately. So a big thank you to Kyle. And then links are here for where you can get the glvnd implementation. And then there's a NVIDIA forum post with a bunch of information on our sort of intermediate complexity around at install time choosing whether or not to use the glvnd enabled driver or not. For distro repackagers, that might be useful information right now, but I hope that becomes not necessary in the not too distant future. So that's all I have. Questions? Adam?
Just from having tried to get this working in Fedora, it runs GNOME Shell with both Wayland and X.Org now. Yay. So it does work. If you write an EGL application and you call EGL getDisplay with anything other than null as an argument, you are a very bad person. Stop doing that. Otherwise, you're handed a pointer, and you have to guess what kind of pointer that display is, and it can't work. This includes the X server, so we need to patch that. As far as like what Mesa needs from glvnd in the future, you now have this weird situation where glvnd installs the libraries that you're going to link against, but you need the headers and the PC files from somewhere, and Mesa ends up being the thing that installs them right now. So we need to shift those headers, I think, into glvnd and have that be kind of the place where you get that. Effectively, for Linux-like platforms, glvnd becomes a build time requirement for Mesa.
Yeah.
I'm okay with that. I think Mesa on other platforms may have bootstrapping issues with that kind of problem. They may want to have its own copy of the GL headers for that reason.
Yeah.
But my concern for non-Linux platforms is fairly low. Server-side GLX, I have ideas I'm going to need to talk about, but that's going to be harder and potentially not that interesting at some point. So we'll find out.
Yeah. The bang for buck there is
pretty low. But the thing that, as far as getting it packaged and into distributions, I think that there's very little left that's not packaging detail.
Yeah.
So I'm pretty excited. Thank you for all the work on it. It's very, very much appreciated.
Yeah, great. Yeah, thank you to Kyle.
Thank you. If I think about the case of AMD, their strategy, well, at least last time I heard, was to have both an open source and a closed source implementation of their GL libraries that could potentially exist alongside each other on the same system.
Right, exactly.
How would glvnd detect which of the two libraries it should use if they are both applicable for the same screen?
It's up to the GLX server-side extension to make that decision. And I think that's a policy decision I would need to defer to AMD.
The server-side extension, GLX ext glvnd, adds another token that you can query for GLX query server string, because that gets already passed in the display and the screen number. So when you ask that screen number, tell me the vendor string, it returns a space separated or a comma separated list of vendor names.
That's right. It's a preferred list.
And so glvnd on the client side will iterate through them in order. Whichever ones you have installed will be the ones that work. There's an X.Org.conf option to set that per screen. So that's already there for Mesa. If you wanted to, anybody else who was implementing this would need to wire up the equivalent option for their screen. But that's how that works, is you just have a client list. This also gives Mesa the option, and other implementations, if somebody really wanted to rewrite OpenGL for their chip, you could do the same thing. Like right now, we just assume Mesa is the thing that's going to work, and we just kind of hard code that string. If you wanted to shortcut something, maybe you get slightly better dispatch performance by optimizing away part of the Mesa common code, you would have the ability to say Intel, then Mesa, then whatever. So that's the way that extension's specified to work.
Thank you.
So you
for sure. Yeah, so just write your name there, and when I know basically how many people are coming, then I can try to plan something that would be nice for everyone. Until then, yeah, I don't know, maybe there's going to be 10, maybe there's going to be 50, I have no idea. So it does change a lot of plans. So please register. And yeah, if you want, you don't have to, you know, just read and copy. You can also do it online by connecting to the website there on the left. VST yeah, so there you will be able to copy paste everything. And if you want to put comments, you can write other stuff there. Okay, seems like everyone is sort of in place. So I'm gonna hand it over to Andy.
Oh, can you hear me? Yeah. Yeah. Okay, so sorry, I'm going to be giving several more presentations. My next presentation is on material that Alex Goins at NVIDIA has worked on over the past year for prime synchronization. So in R&R, prime output slaving is the idea of having two different GPUs, one that's rendering and producing pixels, and another GPU that's consuming those pixels and then sending them out to a display. And typically we use a gem shared buffer for the intermediate transport for that. This is useful in several configurations. Optimus laptops that have integrated graphics and a separate discrete GPU where the integrated graphics is what's connected to display. USB display link adapters, and then also more recently desktop motherboards. Some system BIOSes offer an option to take advantage of the integrated graphics on the motherboard even when you have a discrete GPU plugged in, advertises iGPU multimon. So to state a little bit of terminology up front, since I know it can be confusing, in prime output slaving, the output slave is the GPU that's driving the display. It's receiving pixels from the output master. If you're used to thinking in terms of DisplayPort or HDMI, you can think of this as the sink. And for this discussion, this presentation, typically this would be the Intel integrated graphics. Then on the other hand, we have the output master. This is the GPU in these configurations doing the rendering. It delivers pixels to the slave GPU. Again, in DisplayPort or HDMI, if you think about it that way, you can think of this as the source. And for this presentation, this would typically be the NVIDIA discrete GPU. So until recently, prime output slaving was normally unsynchronized and single buffered. So in this configuration, you'd have an initial handshake between the output master and the output slave. They would agree on a single screen-sized gem buffer to share. The output master would write to this buffer at an arbitrary point in time, maybe in response to individual damage events, or maybe batched up in some way. Similarly, the output slave would read from this at somewhat arbitrary times, typically driven by the memory fetch pattern of its display engine. And of course, this lack of synchronization results in tearing. So to solve this tearing, there's several steps we took. The first step is to make it explicit when the master should update the shared buffer. So we added a new screen rec function pointer present shared pix map. So instead of the master delivering pixels to the shared buffer whenever it wants, instead the slave calls the master's present shared pix map function, and then in response to that function call from the slave, the master will deliver the next frame of pixels into the shared buffer. So this is better, but it's still inherently racy because the actual delivery of that data into that shared buffer
is still not really synchronized with scan out from the slave. So the next step is to double buffer that to address that particular race. So in this configuration, the X server R&R code would allocate 2 gem buffers, and it would then call the output slave, calling enable shared pixmap flipping instead of a previous function pointer that was available, and then the output slave then alternates between these 2 buffers, and for each one in turn calling the master's present shared pixmap function to have the master update the next frame, flip to that buffer, update the next buffer, flip to that, and so on. So the next step is to improve the idle case. So in the configuration I've described so far, typically the slave would require getting a vblank event every vblank, and then in response calling the master. But if there's nothing actually changing, you don't want to, it's wasteful to wake up every single frame at an idle desktop. So instead we added 2 more function pointers to the screen rec. One, a request shared pixmap notify damage, and then shared pixmap notify damage. And so the idea with this is that the slave will call the master's request function when the system seems idle, and then when the master later on receives damage that now something has changed and the desktop is no longer idle, then it notifies the slave, and then the slave can request the next frame to be updated in shared memory and then flip to that. And so here's a diagram showing a little bit of this control flow. So the initial setup for this is the X server allocating 2 gem buffers, then the X server calling the master's share pixmap backing function, which will export each of those buffers to make them available to the slave. Then the X server will call the slave to give it a chance to do bookkeeping. Typically this would be where the slave would register these buffers with DRM KMS. The X server will then call the master to give it a chance to do bookkeeping, to start tracking the damage regions to be able to update these buffers. And then the X server would call the master's present shared pixmap to populate the first of those shared buffers. And then finally, as part of the mode set, the output slave will then flip to that first buffer and request a vblank interrupt. Or vblank event up to user space. And now that the system is bootstrapped and the pump is primed, when the slave receives vblank notification, then it can call the master's present shared pixmap to update the next buffer. At that point, the master looks to see if there's been any damage to the region of the screen that will be used for that next buffer. If there is new content, then the master will copy content into that buffer and return true, at which point the slave will then schedule the next flip to that buffer. If, however, there's not content for the damage region that the master is tracking for that buffer, the master returns false, and at that point, if we've implemented the mechanism, or if the master has provided the mechanism to request damage notification, then the slave can call back to the master to request to be woken up when damage has happened. And if we have that much, then the slave can return from that call chain, and it'll eventually be notified. Otherwise, if the master hasn't provided that, oh, I'm sorry, I've got that backwards. If the master, in I1 here in the diagram, if the master does not provide the request function, then the slave needs to request a vblank event and then go to sleep, and when that vblank event happens, then we return to step G. If the master does provide the request function, then the slave can call that and return, and when the master receives damage, it'll notify the slave, and then we go back to step G again. So far so good. The next step after that, though, is to synchronize the actual flip in the slave with the GPU work in the master to make sure that the ordering is correct. So typically, you wouldn't want, in the master's present shared pixmap function, you wouldn't want the master to wait on the CPU for the GPU work of doing the copy to actually complete. You would normally kick off that work, let the GPU do its thing, and in parallel with that, return on the CPU to the slave, who will then schedule the flip. But we need to ensure that the slave's flip doesn't happen until after the GPU work has completed. So here's a diagram trying to better illustrate the problem there. So you can see here at this point in time, we're currently displaying frame n, the content of frame n, which is in display, is in buffer A. The slave has called the master, and the master has done work on the CPU to kick off the GPU to do the copy, and that gets kicked off. At that point, the control flow returns back to the slave, and it schedules its flip, and then the GPU work progresses to do the copy. So frame n+1 has been copied into buffer B. The flip happens to display buffer B, and so now we're displaying the content frame n+1. We do the same thing again for frame n+2 to buffer A. Then at that point, we display frame n+2 in buffer A. But if for any reason anything in the system gets slowed down, any other scheduling happens, such that the GPU work, well, such that the master kicks off the GPU work, returns, the slave schedules the flip, but then the flip happens before the GPU work actually completes. Then at this point in time, we'll flip to display buffer B, but buffer B still contains frame n+1's content instead of frame n+3 until the GPU work completes here. So really we need to ensure that the flip here does not happen until after this GPU work completes. So the solution for this is fencing. So we use a fence to block the flip until the master's work on the GPU completes. So the master attaches a fence before doing its GPU work to update the buffer, and when the GPU work completes, it signals that fence. So we updated the Intel kernel driver to honor fences when flipping, and that was included mainlined in time for Linux 4.5. Now one of the other pieces to make the system work properly, you really want the master's OpenGL rendering when synced to vblank to be throttled to the vblank of the slave, but we don't have a clear communication path there. But with the mechanism I've described so far, the operation of the master copying from the X screen to the shared buffer is effectively like a virtual vblank for purposes of OpenGL. So within our OpenGL implementation, when OpenGL is syncing to vblank in this configuration, it treats NVIDIA's present shared pixmap effectively like a virtual vblank and is throttled to that. That's going to be fairly implementation dependent from one OpenGL implementation to another, but it's good to be aware of this. And as part of, to further support that, the CRTC pointer is passed into one of the other functions when this is set up in the master, so that when OpenGL is configured to sync its vblank to a particular output, it can correlate that output name to a particular R&R CRTC. So, in this example here, if HDMI 0 is an Intel, is a slave output, but this is running on the NVIDIA OpenGL implementation, we can recognize that that we're syncing to that particular present shared pixmap sequence. So the status of this, the mode setting X driver has been updated to support prime sync both as an output slave and as an output master. The NVIDIA X driver has been updated to support being a prime sync output master. And within the X server, given a new enough X server, and when both drivers involved support all of this, then we automatically enable prime sync. But that can be disabled if you want through an output property. So for future work, in theory, what I've described for the mode setting driver should work on top of any DRM KMS driver. We've really only tested it on top of the Intel driver. The one piece that we know would be missing elsewhere would be the fenced flipping. So that's something that should be implemented in other DRM drivers. Unfortunately, at runtime in user space, we don't have a good way to detect if the DRM driver involved supports fenced flipping or not. So that's what it is. We've also found the USB devices don't provide a very reliable vblank so the mode setting driver actually blacklists USB devices for purposes of prime sync. And reverse prime would require more work. The case where the output slave isn't an integrated graphics that can read from system memory, but instead has discrete video memory. Instead, in that sort of case, the GPUs would need to copy from the gem shared buffer back to shadow video memory, and that sequence would need to honor fenced flipping as well, or rather fenced copying. And so thank you to Alex Goins, who did most of the implementation work for this. I'm just here presenting the slides. And Alex has provided some more end-user focused documentation on how to configure this in the forum link in the slide deck. That's all I have on this. Any questions? Yeah, we'll grab the mic. I think Eric had a question.
So do we have any tests, or could we write tests to make sure, in IGT, to make sure that the drivers actually do the appropriate fence weights at flip time?
I don't think we have any unit tests for that today, but
should
could
be
be
doable though, right?
Yeah, certainly. Pass it back to Daniel.
The CRC-based stuff to check that what you displaying is actually what you think you're displaying, that Collabor has been doing, should land in 4.9 hopefully. And we have some, I think, still non-generic test cases that use vgem to test the syncing with the fencing with foreign fences and objects. So, as in,
sorry, could we get, is there a second microphone? We can get that to Eric.
I guess we can talk about this later on.
Sure,
That's
sure.
probably better.
But I guess the point is that we could use CRC-based checking to help that unit test.
Yeah, it would be nice though to have coverage, if possible, to make sure that all drivers support it, even if you don't have CRC-based checking, which my hardware doesn't.
Yeah.
And also, I'm pretty sure I'm not doing the syncing like I'm supposed to. So I was thinking we could probably implement a test that's something like set up a DMA buff with a fence that is to be signaled, ask to flip it, see if the flip ever happens, and then eventually, you know, once we've decided that it hasn't flipped early, then fire off the fence.
Yeah.
Seems doable?
I think so.
I think we have the interfaces for this.
That should work.
Yep.
Does this prime output slaving work correctly if on the sync side the resolution changes in the middle of rendering?
That'll be, I think, a mode set from the R&R perspective, and I think the X server would tear down the current configuration and rebuild the new configuration. So yes, that should work properly.
Okay.
Okay.
Very good.
Great.
Thank you.
Thank you. All right. I unfortunately do have one more presentation. Do we want to jump right into that, or?
Well, I guess we just had the break, so we could have a bigger break afterwards.
Okay,
so
I'll
go for it.
All right, sure.
then I'm done. Okay, so I'm going to take a few minutes and talk about HDR, high dynamic range. This is, I should give a disclaimer first. I am very much not a color expert, so when I get into chromaticity and stuff like that, feel free to correct me. I'm definitely not an expert in that. So high dynamic range is something that NVIDIA has been seeing requests for from a variety of customers. It's something that NVIDIA's invested effort in so far that we've implemented in our Windows driver and our Android driver. We've not yet implemented this for our discrete GPU Linux driver. So I've been doing some investigation and reading to better understand what HDR would mean for Linux. So this talk is mostly just presenting what I've learned so far, and there's a bunch of links at the end if you're interested to read more about this. It's here. Yeah, so I'll just present some building blocks and try to raise awareness of the basic pieces that go into HDR. So the trend right now we're seeing is ultra high definition displays. Is the next generation of TVs and display devices, and I think there's three interesting new things they bring: that you get higher pixel resolution, 4K and 8K resolution, wider color gamut. For the sake of time and simplicity, I'll try to avoid talking much about color gamut, except where it directly interacts with HDR. And then the third piece of ultra high definition displays is high dynamic range. The idea of being able to express a wider range of luminance than what displays can do today. So if you read about HDR, one of the specifications you'll see referenced a lot is ITU-R 2020. You'll see it called Rec 2020 or BT 2020. And this specification defines a lot of different things about ultra high definition displays. So it gives some recommendations for particular resolutions and refresh rates. It specifies particular chromaticity. I'll talk about that a little bit in one of the next slides. It describes particular signal formats that should go across the wire to the display in terms of full all-component RGB or chroma subsampled YCB-CR. It talks about recommendations for particular digital representation, 10-bit or 12-bit going across the wire, and it describes particular transfer functions that should be used. And I'll go into what the transfer functions are a little bit later. You have to infer a little bit from context when you read HDR documentation. When people say BT 2020, often they're referring specifically to the color gamut that's recommended by BT 2020. So just be aware of that sort of thing and infer from context. And I guess another thing to note about BT 2020 is that it is a set of recommendations. It's not a hard and fast compliance requirements. Other specifications that dictate compliance will refer to bits and pieces of BT 2020. But in terms of BT 2020 itself and the color gamut that it recommends, very few displays today can get close to that. There's a different color gamut that's slightly smaller, DCI P3. And the current generation of ultra-high definition displays are much closer to that. So since I mentioned chromaticity, so when we talk about different color spaces and these different specifications, they all describe different color gamuts. And I guess the way to think of a color gamut is the CIE organization a long time ago defined a theoretical three-dimensional color space, XYZ, where the Y axis described luminance. And when you see diagrams like this, with this horseshoe shape, this is a 2D projection of that CIE XYZ space. So a 2D projection of this 3D color volume. And typically this is called the CIE XY chromaticity diagram. When people describe different color gamuts, they'll give 4 coordinates within this 2D projection.
the XY location of the red, green, and blue primaries, and white point. And what those locations of the primaries mean is how green is 100% green within this color gamut, and how does that compare to other color gamuts. So that's and same for red and blue. So the chromaticity coordinates are describing how bright each of those or how saturated each of those colors are when it's described as 100% within that color space. And pretty much all the color gamuts we'll look at have the same white point, which is dubbed D65. So to cover one other piece of background, an important thing to be aware of is the difference between a linear color space and a nonlinear color space. So in a linear color space, the numbers that you store to describe colors have a linear relationship to the actual colors they represent. So that has the nice property that when you double a number describing a color, the actual intensity of that color correspondingly doubles. And this is sort of intuitively what I think we would expect. And so when you're doing any sorts of graphics operations, blending and scaling and those sorts of things, you really want to do it in a linear color space so that the resulting numbers make sense. And there's some links at the end of the slide deck to articles that go into a lot more detail explaining what goes wrong if you try to do your graphics operations not in a linear color space. So linear color space is good for doing graphics operations. However, a linear color space is less good for digital storage. Human perception is not linear, where our eyes are more sensitive to darks than lights. So given a fairly small number of discrete steps, say 256 for 8-bit per component, a linear representation stored, a linear storage of that color is not great. It gives you insufficient granularity to describe all of the different darks that you can see, and it wastes precision in the lights where you can't tell the difference as well. So generally it's recommended to store colors in a nonlinear color space, and the most ubiquitous nonlinear color space we have today is sRGB. Most pre-HDR displays today expect their input to be sRGB. Okay, so now we get finally to HDR. So high dynamic range, informally you can think of it as gives you a way to describe things such that your brights are brighter and your darks are darker, and you can see more detail in both the darks and the lights. More formally, HDR increases the range and granularity of luminance. Luminance itself is a measurement of intensity over area. When people talk about the units of measurement, it's candelas per square meter, but normally you see people refer to it in units of a nit. Standard dynamic range, SDR, so pre-high dynamic range, your maximum nits are around 100. The first generation HDR displays we have today are around 1,000 nits, and the HDR specifications that we'll go into in future slides allow a maximum of about 10,000 nits. For reference, I think the sun is like 10 to the 9th nits if you were to look at the sun at noon on a sunny day. I don't recall other reference points right now, but you get the idea. And I guess the other thing to be aware of with HDR is the point is to allow the highlights in a scene to be brighter, not necessarily to make the entire scene brighter. It's not like we want to take an SDR scene and scale it by some factor to make the whole thing brighter. Really, most of what we look at today on a monitor is about the right brightness, but we want more granularity, and we want to allow highlights to be brighter than what they are today. So HDR in rendering is not new. It's a technique that 3D applications have been using for a while now. And the typical flow in a 3D application that's using HDR rendering will be to create an FP16 buffer, so half float, 16 bits per component, and render to that FP16 buffer, taking advantage of that larger range and larger precision. And at the end of the graphics pipeline, when the application is ready to display that, they'll use a technique called tone mapping to scale that FP16 content down to something that's lower precision and lower luminance to be displayed on current display hardware. So typically 8-bit per component SDR. But now that we have more capable displays that are capable of displaying HDR, we want to get from HDR rendered content and be able to carry that through and present that to the HDR display. So we'll review this flow again after I describe some of the things mentioned here, but as an introduction, the basic flow from a 3D application producing HDR content to displaying it is this sequence. And I'm glossing over a bunch of details, but at a high level. The application will create an FP16 buffer and render to it in a color space called sRGB. Then it will tone map that content from sRGB FP16 to the target monitor's capabilities. And we'll talk a little bit more about that in a few slides. The application will also provide metadata to eventually be provided to the monitor that will describe characteristics of how the application rendered this scene. Then something in the system, if we have both HDR content and SDR content, someone will need to composite the two together to produce a single image to send to the monitor. Then at the driver level, we would take this sRGB FP16 image, and we would perform something called an inverse EOTF to encode that FP16 in a digital signal to send to the monitor. And then send both that digital signal and an info frame to the HDR monitor. The monitor will then receive the info frame and the encoded digital signal, decode that, and then convert that to the image to actually be displayed on the monitor. So now in the next few slides, we'll talk about what these different steps mean. So first, sRGB. If you read HDR documentation, you'll also see this referred to as the canonical compositing color space, CCCS. sRGB was something that was introduced by Microsoft, I believe in the Vista timeframe. The idea of sRGB is that it has the same chromaticity coordinates. If we went back to that diagram, the chromaticity diagram, sRGB has the same coordinates as sRGB, but sCRGB is linear as opposed to sRGB, and sCRGB has several encodings. For our purposes, the interesting one is the FP16 encoding. The values in the range 0 to 1 in sCRGB correspond to sCRGB if you made it linear and represented it in 0 to 1, and that correspondence between sCRGB and that correspondence between sRGB and sCRGB will be very powerful later for compositing purposes. But sCRGB is a superset of sRGB in that it can store values outside of 0 and 1. It can store things in the entire range of FP16, which is, I think, negative 64K to positive 64K. So values out, if the range 0 to 1 in sCRGB corresponds to sRGB's chromaticity, values outside of 0 to 1 extend the color gamut relative to sRGB. The other thing with sCRGB is that the numbers describing it are absolute rather than relative. And so you can think of that as if you were storing 0 to 1 and we're interpreting that as relative, you might interpret 0 as the darkest thing the monitor can display, and 1 as the brightest thing the monitor can display. But instead, if you were treating that as absolute, you might interpret 1 as 80 nits, comparable to what an SDR display can do today, and you might interpret 12.5 in FP16 as 1,000 nits. And so this overlap between sCRGB and sRGB make them good for compositing together HDR content and SDR content. Another piece of this is the metadata. The SMPTE 2086 specification defines a set of things that are important to know when you're talking between the GPU and the application and the HDR monitor. So one, there's the chromaticity coordinates describing the color gamut of each of these pieces in the pipeline. There's the maximum luminance that can be displayed on the particular monitor and the minimum luminance that can be displayed on the particular monitor. The GPU and really the application needs this to know how to render the image and the range of values in sCRGB. Remember, it's absolute, knowing what range of values makes sense for this monitor. And the monitor needs this information from the GPU to know how to interpret the signal that it receives. And so there's another specification, CEA 8613, that defines how the HDR metadata defined by the SMPTE spec is encoded, both in the EDID, so that the display can report the metadata to the GPU and the application, and encoded in the info frame so that the GPU can report it to the display. Okay, so transfer functions. If you read HDR documentation, you'll see a lot of references to EOTF, which stands for Electro-Optical Transfer Function. This defines how the display receiving a digital signal from a GPU should translate, that is nonlinear, should translate that digital signal into linear light values to display on the screen. This encoding is optimized for bandwidth. It compresses the signal from something relatively large like FP16 down to typically 10 or 12 bits. But it takes advantage of, again, remember, the human visual system is more sensitive to darks than lights, so you can compress by using less bits when you're describing lights and more bits when you're describing darks. Compressing by sacrificing bits, sacrificing precision where we don't need it. For SDR, sRGB is the de facto transfer function. In HDR, there are two transfer functions you'll see referenced a lot. The first is something called the perceptual quantizer. You'll also see it referred to as PQ. That's defined by the SMPTE 2084 specification. The other transfer function you'll see reference to is the hybrid log, or HLG transfer function. So to create the digital signal that the GPU is going to send to the monitor, it needs to do the inverse of this transfer function to encode it, and then the display will apply the transfer function to decode it. You may see the GPU side of this referred to either as inverse EOTF or OETF. Okay, so here's the high-level control flow again, and hopefully it makes a little bit more sense now, having described some of those terms. So again, from the application standpoint, it will create an FP16 buffer and render into it using the sCRGB color space. If the sCRGB color space can describe a very large range of luminance, but the monitor reported through its EDID that its luminance is maybe only 1,000 nits as opposed to 10,000 nits, then the application can use that luminance range as input into the tone mapping algorithm that it uses to convert the full range FP16 down to a range that makes sense for the target monitor. And it is important to note that the application at this point is producing content intended for a particular monitor. And then the application will needs to provide the information about, here's the luminance range I was targeting when I tone mapped this. Provide that metadata down through the call stack so that it can eventually be provided back to the monitor. Then either the driver or potentially a composite manager may need to composite this HDR content with SDR content. And again, taking advantage of the overlap and correspondence between sRGB and sCRGB, we can do that compositing in FP16. So once we've composited and then have a resulting FP16 image, then the driver needs to apply inverse EOTF to encode that, to encode the incoming FP16 from the application, produce the digital signal that'll go out to the monitor, and then send both the encoded digital signal and the HDR info frame to the monitor. The monitor then gets the info frame to know how to interpret the digital signal, and then applies a transfer function to decode that signal, and then finally display the image on the screen. Okay, so what does all this mean for Linux? So there's a few pieces that we would need to figure out how to fit into the system. So one, I think, so applications already have the means of creating FP16 buffers and rendering into them, so that much is good. But the application will need some API to get HDR metadata from the display. That's contained in the EDID. Conceivably, we could just have a client-side library that parse the EDID and applications could get the information there. But it probably requires a little bit more thought to think about if drivers will ever need to influence, I guess either drivers or composite managers or anything else in the system between the hardware and the application. If anything in that stack needs to influence the monitor's capabilities advertised to the application. I guess that would influence if it's just a raw parse the EDID and let the application do it itself, or if the stack in between needs to be able to control and potentially downgrade the capabilities reported to the application. On the other side, the application needs to have some way to communicate the HDR, the luminance range and other HDR metadata that it used producing the image, and pass that down the stack so that eventually the driver can feed that back to the display. And there again, we need to think about if anything in the call chain needs to be involved. Where I imagine it gets complicated is if you had two HDR applications inside Windows, inside separate windows within a desktop, each making different decisions about their HDR-ness, and if they were communicating different luminance ranges down, and then someone had to do some sort of arbitration. I'm not really sure what that would look like. And I should note, so far, NVIDIA's Windows implementation of HDR is full screen only. But one would imagine, taking advantage of the compositing that we can do in sCRGB, one would imagine that eventually that could be handled within a composited desktop. Assuming an application can render to FP16 and produce that image, do tone mapping based on metadata it gets from the display somehow, and the application can provide metadata that should eventually go back to the monitor, we still need some way to actually display that FP16 content. We need some path for being able to pass an FP16 buffer down the stack to the driver. Today, NVIDIA's hardware doesn't have native support for doing the inverse EOTF. I don't know if anyone else's hardware currently does. One would expect that eventually hardware will be able to do that natively and could just take an FP16 buffer. Until then, we would need to use a shader somewhere in this stack to take that FP16 buffer, do the inverse EOTF, and produce the 10 or 12-bit per component encoded thing that will go across the wire. And again, it would be nice if we could somehow support compositing SDR, current RGB8 windows with HDR windows and composite that together into a single desktop. So if we were doing this in something like Wayland, presumably the Wayland compositor would need to be FP16 aware and need to be able to accept FP16 buffers from its clients. It would also need to be able to composite together SDR RGB8 content with HDR FP16 content, producing a single FP16 buffer that would then be passed down the stack, and would also need to be able to flip to that FP16 buffer. If we were doing this within X11, I guess we have to decide, do we care about X rendering to an FP16 buffer? I don't think the primary producers of HDR content are likely to include X. Presumably it would be 3D applications like OpenGL and Vulkan, and video drivers like VDPAU and VA API. So I don't think we strictly need X rendering to FP16, but I guess it's a question of, is it easier to somehow prohibit that rendering, or somehow define what the right semantics are in that case? Maybe you could do crazy things like within the driver hide a conversion from current 8-bit per component rendering to an FP16 buffer, such that from the client's point of view, it thinks it's normal 8-bit RGBA like today. Depending on the answers to the above, should the root window be capable of being FP16? Or alternatively, should we have an FP16 overlay visual, similar to the old school 8-bit color index overlay visuals of the past? If we went that route, maybe when the FP16, if you had an FP16 window, created with an overlay visual, in that case it could be the driver's job to composite the things together. If the window were not redirected. But if the window were redirected to a pix map, then presumably it would be the composite manager's job to composite things together. If we had an FP16 overlay visual, I guess that would give composite managers a path to creating a child of the composite overlay window that was FP16, and composite the whole scene together as FP16 into that, and then display that. But clearly there's a lot of unanswered questions there. So anyway, I don't have answers to any of this yet. Hopefully these slides give some context about what HDR is, and familiarizes you with some of the terms. I found the terminology pretty hard to understand at first until I read into it more and started making a glossary for myself. So hopefully this helps if you want to, gives you some context if you want to read more. And there are a lot of open design decisions that need to be made for this. So I think this is something that NVIDIA is certainly interested in. So we're going to give this more thought and brainstorm. Hopefully we can have some conversations about it here at XDC. I hope to be able to make some straw man proposals at some point, and we'll see where the conversations go. So yeah, if you have thoughts or feedback, we can talk about it now, or grab me sometime over XDC, or my email address is here. The next few slides have links if you have a transatlantic flight and want to read a lot of stuff. There's various specifications. I guess there's specifications on the next slide. And then here there's some white papers and blog posts on things about HDR. The HDR demystified PDF I found pretty good as an overview. And then NVIDIA has provided some documentation geared towards 3D game developers on how to take advantage of, assuming you're already doing 3D you're already doing HDR rendering, how to take advantage then of HDR display. That PDF is pretty Windows-centric, but given that that's how application developers are being steered now and will want to encourage those applications to port to Linux, we should think about what the porting path would be. And then these are some articles about linear RGB versus sRGB that are pretty interesting. And some specifications if you want to fall asleep on the plane. That's all I have. So I don't have questions about any of this. Let's grab the mic.
Hey, so there are movies out there that are in HDR, 10-bit depth or 12-bit depth.
Yeah.
And on Windows it's quite easy to render them. And as I understood you, it should be quite easy to do the rendering as well on Linux. But the hard part is actually to display it at all, because we have no metadata at all.
Well, thank you for bringing that up. I was pretty focused on 3D rendering of 3D produced HDR content, but you're right that there's a lot of existing video content that's HDR. And my understanding is that in those cases, those streams carry HDR metadata with them that describe the display on which that content was mastered. And so that's one of the reasons why it's important to be able to provide HDR metadata back to the display. It's not just that the display says I can do this luminance range, and if software, if the GPU was required to always match that luminance range, then we wouldn't really need to provide an info frame back. But because we can get content, from a video source that was mastered, targeting a particular luminance range, the idea is that you should be able to provide that stream along with the metadata that describes how it was mastered, and feed that back to the display, and then the display is supposed to deal with that.
But the last part is the thing we can't do as of now, right?
Correct. Okay. Yeah.
Okay. Another question. Here.
Oh.
Yeah. Have been any thoughts of moving the tone mapping to the compositor?
I think that's possible. I hesitate a little bit to do that. So I didn't talk much about the tone mapping process, and I admit I don't know in much detail myself. My impression is that there's a variety of different algorithms and techniques for that, and NVIDIA, our dev tech working with game developers, have put together a set of recommended tone maps, tone mapping techniques that we recommend for game developers that take targeted luminance range as input. So it's this parameterized thing. But my impression is that there's some artistry to tone mapping, and for that reason I think you want to the extent reasonable, leave that to the application to make artistic decisions as part of the image that they're producing. But it may be that we give the application the choice. If you want to do the tone mapping and do whatever cosmetic, artistic decisions as part of that, you can. But if you don't, and you want to just give us FP16 in the full range of FP16, then the composite manager or whomever else can optionally do the tone mapping. Maybe that would be a reasonable compromise. I don't really know yet.
The point is that if it's full screen, then there's no problem. The app can do it. But if you have, for example, two streams together, then maybe some way of arbitrate that is that the tone mapping is done after the apps.
Yeah.
But yeah, for the full screen case, the application should do it.
Yeah, yeah. And I think that the two HDR applications viewed at the same time is going to be the particularly hard case. I agree.
Thanks.
Okay. Jason, you had a question?
Yeah, so you might have said this and I probably just missed it, but with the conversions, so we have these different standards of dealing with FP16 data, and you said that they're specified as absolutes where you have certain nit values for different floating point values.
Yeah.
With that mapping, is there also a recommended mapping for how non-HDR data is supposed to compare to the HDR? Is it just 0 to 1
Yes.
as usual? Okay.
Just 0 to 1, yeah.
Okay, that makes combining things a lot easier.
Yes, yep. I guess to application developers doing HDR, those 0 to 1, I think makes sense, is what we recommend as a default, but our dev tech also cautioned that there are cases you can imagine if you had a HDR content with a very bright highlight and you composited a translucent SDR on top of that, the SDR would get completely washed out. And so in the case of an application that has done HDR rendering and has highlights, but then wants to present SDR UI elements on top, we recommend scaling back the brightness on the, scaling back the luminance on the HDR content that's going to be composited with SDR on top. So it's not as, I suspect there'll be cases like that that won't work well unless we take some extra steps. Yeah, yeah. Okay.
So doing this in X11 is really, really achy.
Is that sarcasm?
No, it's
Okay.
it's a property of the wire encoding. When the way visuals are described right now, you have red mask, green mask, and blue mask that describe where the bit channels are.
Yeah.
Those are int32.
Yeah.
If you have 16-bit floats, you don't get to describe those accurately. Now, you can create some new thing that's like a visual that only applications that know about this particular extension would see, and we could just hide those windows from the rest of the window tree.
Yeah.
We could add a new visual class to go along with true color and direct color that redefines the interpretation of those bits and somehow give the application a way to like key into that so that they don't accidentally pick up the wrong visual class. And reinterpret the root window connection block about that. But as written, it's hard to pack FP16 windows into the X11, and which is why like the old SGI extensions for a bunch of the high dynamic range and for doing YUV colors and this kind of thing operated on P buffers.
Yeah.
And they had a special extension for present this P buffer this way.
Yeah.
Because there was no other way to get the right kind of format information at all. This is not just getting the right format information, this is also bringing along this other chunk of metadata. So.
Right, right.
So my advice is to just ignore that this happens on X11 and target a better window system.
Yeah. Yep.
But it's still going to, the representation problem is still going to be hard.
Yeah, yeah. Do you think it would be difficult to somehow prohibit or just ignore any X rendering to an FP16 window?
It's very easy to not service rendering requests. Yeah.
Yeah. Yeah.
That's return.
Yeah. But I mean, to have to sprinkle special case checks everywhere.
If you want to, if we create a new pseudo window object that simply doesn't get, that you can't talk about unless you're using the HDR aware extension for talking about the window tree, then and you just expect you have to be running a window manager that knows about this in order to be able to get those windows to exist at all.
Yeah.
That's pretty straightforward. We can just hide bits from the window tree. That's not terribly difficult. But trying to bang them into like the existing visual list is going to be really difficult. So
yeah. Good. Thanks.
So what's the story with the screenshots of AGR content?
Yeah. I think the screenshot application would need to be aware of the FP16 format. I imagine. I haven't given it much thought.
But how would that work on X11? Because of the topics already highlighted.
Yeah.
For the visual type and so on.
I mean, yeah. I mean, I guess reading from an FP16 window with something that isn't HDR aware would have the same problem as writing to an FP16 window with something that's not HDR aware. And so presumably you would just read back black in that case. I don't know.
As far as I understood, on Wayland, it doesn't make any sense to have an actually screenshot application, but it's part of the compositor, or it's way easier to make it part of the compositor. So if the screenshot application is part of the compositor,
and the compositor is HDR aware, then
we know that it's an
falls out
HDR
naturally.
application. So it would be really easy to make an HDR screenshot on Wayland if we had all the other bits.
I would disagree, because the question is whether we want an HDR screenshot or an SDR screenshot. So maybe we have to create a new interface to let the user or the application who requests screenshots, for example, Firefox for video sharing sites, to decide.
We'll have to see. I do imagine that whatever, either prohibiting things or adding new extensions to interact with FP16 windows, writing to them for any sort of rendering and reading to them I imagine will have the same constraints and same prohibitions. Okay. Anything else? All right. Thank you very much.
to your seats. I'm sorry for the coffee. The situation is gonna be, fixed soon. It's gonna come back. Oh, there's still cake, yeah.
Okay, should I start?
Yeah, I
Okay.
guess you can start. Okay, everyone, sit down. Please, please.
Okay. This is Miguel from NVIDIA. This is my first time here at XDC. And I'm going to introduce you this work in progress project that I've been working on lately. This is the outline of my talk. I'm going to give a few points of motivation of why we want this EGL external platform API. I'll give an overview of the API, how it interacts with libgl, and I'll describe how we implemented a few functions to add support, Wayland support, using this approach. So, the main motivation is to decouple platform drivers from EGL drivers, such that anyone could write new Windows systems and add these platform drivers to integrate with existing EGL hardware drivers. That way, we wouldn't need a vendor agreement to support non-well established Windows systems. Also, the platform code could be open source, even if the EGL drivers are not. So less closed source is a win. And one common platform implementation is improves consistency. It's better to have only one place to fix bugs. So we want a specification of an API for writing EGL platforms and their interactions with modern Windows systems. The idea is these external platforms to use only application-facing EGL functions. In such a way we can leverage config selection, context creation and rendering support from lower-level EGL platforms such as GVM or EGL device, etc. Or even we could implement newer external platforms on top of more complex platforms such as X11 Wayland or Android. The way EGL talks to external platforms is through a set of functions that are provided as an export table. I tried to group all these functions in these several types. We got pure EGL hooks, derivatives of EGL functions, external object validation functions, and handle translation functions. Communication the other way around from external platforms to the EGL implementation should happen mostly through application-facing EGL functions, but there are several cases that we need some, let's say, workarounds, or we need to run non-conventional or non-application-facing code. So we added these callbacks to the API. So pure EGL hook is basically a direct replacement of an application-facing EGL function for resource management. Some examples of these functions are the EGL get platform display, EGL create platform window surface, or EGL swap buffers. So basically, libgl would forward calls to these functions to the EGL external platforms. The derivatives of EGL functions are they are very similar to EGL functions, but they address like subparts of the application-facing EGL functions. An example of that is the query string function, because libgl would require to get what extensions every external platform is implementing and merge them together to provide a single string to the application. Then we got the external object validation functions. These are required to basically figure out what platform should handle several EGL calls. For instance, if the application call EGL get display with a native display handle, we don't really know what external platform should handle this call. So we could use the isValid native display API to determine what platform should handle that call. The same happens with EGL create image or EGL create stream attribute. So we added this rstream attributes external to decide what external platform should handle those calls. Then not every single EGL function is implemented by the external platforms, so libgl needs some way of translating external handles into internal ones, so we need at least a get internal handle API to do that job. As I mentioned earlier, there are several operations that require non-application facing EGL paths. We added a register callback API to this external platform API. And an example of this path is setting EGL error codes. We want the application to be able to catch EGL errors happening within the external platform, so we can let the EGL driver to register a callback for such purpose, and the EGL external platforms could use this callback to set EGL errors. So how this all interacts with libgl. External platforms would be separate libraries. So discovery and registration of EGL external platforms is libgl's responsibility. We recommend to use a portable and fully configurable discovery mechanism like libglvnd does with JSON files. And the very first interaction between external platforms and libgl happens with this load external platform function that takes the version of the EGL external API libgl is going to use. That way, the external platform may know what kind of functions it needs to export, fill out the external platform export table, and then make sure that libgl is going to work fine with that external platform. Otherwise, this function could just fail, and that external platform would be ignored. Here's an overall picture of how this all would look like. An application would use application-facing EGL APIs. The libgl entry points would decide if that's an external platform or not, and then use the external platform API to call into the EGL external platforms. And in turn, these EGL external platforms would call back into libgl using application-facing EGL APIs, which, in case they need to be addressed by internal platforms, libgl would redirect them to the driver internals. And there's another path coming from EGL external platforms to the driver directly, which are these EGL external callbacks. So I'm going to give an overall description of a few functions and how we implemented them using this approach to add Wayland support to the NVIDIA driver. I'm just gonna describe how EGL get display would work, EGL get create Windows surface, and then EGL swap buffers, because it's the simplest application workflow that we can run it. So an application would call EGL get display, giving a Wayland native display handle. libgl would run through the whole list of available external platforms, calling the isValid native display API, and the Wayland external platform would answer true. Then libgl would call into the get platform display pure EGL hook, giving the required arguments, and then is when the Wayland external platform would use application-facing EGL APIs to query the available devices, and would call into EGL get platform display to get a display handle for a given EGL device. That handle would be returned back to libgl. And I think I forgot to mention it earlier, but libgl is responsible of keeping track of what handle belongs to what external platform. So subsequent calls can be made directly to the appropriate external platform. Note that since EGL device platform is an internal one, libgl would recognize that and would forward both EGL query devices and EGL get platform display, giving an EGL device to the driver. In case of EGL create Windows surface, an application would give the return display handle in the previous step and native Wayland window handle. libgl knows that this display handle belongs to the Wayland external platform, so it would call directly to create platform window surface, giving the display handle and the native window handle. And as many of you already know, we implemented this on top of EGL streams. So the Wayland external platform would call EGL create stream. It would query these, the stream file descriptor to be shared through a Wayland protocol with the compositor, so it can create the consumer side of the stream. And then it would call into EGL create stream producer surface to create the producer side of the stream. And that surface handle would be the one returned back to libgl and back to the application. Finally, the application would start calling EGL swap buffers, giving the previously created display handle and surface handle. libgl already knows that this surface is coming from Wayland standard platform, so it would directly call into the swap buffers EGL hook, and the Wayland external platform would call into EGL swap buffers, giving the EGL device display handle and the EGL producer surface handle. Yeah, I left all the communication from communication of this external platform with the Wayland server out of this picture for simplicity. But yeah, I think we do a similar thing as Mesa, so we would swap buffers, then attach a Wayland buffer, commit the surface state, and so on. So, as conclusions, we introduce an EGL external platform API to decouple platform drivers from EGL drivers. We successfully added Wayland support as an external platform following this approach on top of the EGL device and EGL stream families of extensions. And the idea is to open source all this soon, so others can benefit of this and suggest improvements and so. Yeah, I got an extra slide here with a picture of how the EGL external API looks like currently, but yeah, it's subject to change. So yeah, and I think in the following weeks, as we try to open source this will probably change a little bit. So, any questions now?
So, EGL streams.
Yeah.
Do you have, just in case that doesn't work out? Do you have some kind of alternate plan with, say, using DMA buff and providing metadata as well to pass images around or anything like that? Or is this sort of quite tightly tied to having streams and not exporting views of individual buffers to the external platform library?
I think, yeah, most of it is going to be probably discussed after my colleague James gives his presentation, and what's the plan to basically address all that issue in the foreseeable future.
I don't think there's anything in the external platform mechanism itself that's tied to streams.
Yeah.
Our implementation used streams. That's the example Miguel was using, I think.
Yeah, we could just, for instance, implement a similar external platform on top of GPM, and then, yeah, provide the EGL image creation APIs required to create an EGL image from a Wayland buffer and so on. But yeah, the underlying driver must support at least the low-level EGL platform to do that. So that's why we ended up going with streams, which is what we support nowadays.
So there is a question on the internet. Does this mean Wayland will be compatible with NVIDIA latest proprietary drivers?
Isn't that compatible already? I mean, we added Wayland support to our driver, and we released some public patches on top of Weston, top of 3, and yeah, there were some users trying that out already.
Yeah, I'm sure what Terence means is probably on GNOME or KDE, and yeah, EGL streams is apparently not going to be accepted there.
Yeah, so
but
I don't know.
The way I will answer this is that you're definitely working on it, and there are going to be discussions
afterwards
today and for the rest of the conference on how to fix this basically and make it happen. So yeah.
So one thing that this and GLVend extend implementation both have this property where...
Can you speak a bit louder?
Yeah, both GLVend has this problem too, where like the way you've described this implementation, basically the libegl has to know, like a platform extension can't add entry points. Your libegl implementation here is going to need to know about every entry point that a platform might expose.
Yeah,
right. This is effectively, platform extensions are EGL client extensions, right? They have to be something that the loader, that API level knows about and is capable of getting an answer from EGL get proc address and getting that back to the application so it can be called.
Yeah.
Am I right about that?
Yeah, more or less. We are having some internal discussions if we want this to be hang of libglvnd. Currently, this is only implemented within the NVIDIA driver, so it's like a thin layer on top of the driver internals that would implement that logic, deciding, loading all the external platforms, deciding which one needs to be called, and so on. Yeah, we are not sure yet if we are gonna integrate this into libglvnd.
Okay.
So that's basically why I just said libegl, and yeah.
So one thing that seems like it should be doable, and I just am not good enough with the tools to do it, is you would think that you could have a table of functions exported from, you've got a list of platform extensions behind you. You have a table in it that describes not only the name of the entry point, but its function signature,
Mhm.
and you construct the function call with FFI or similar, and hand back a code-gen instance of that. So that way a platform backend could add its own function entry points as well as adding in all the places where you've already got, hooking off this enum for indirect lookups or object validation. Is there any way I can bait somebody into implementing that for me? Because it'd be great.
No, I don't think I understood correctly the last part.
FFI is foreign function interface. It allows you to programmatically construct a function call to some function pointer with these arguments in this type and pack the arguments in and out. And the idea is you're supposed to be able to use it for generating function calls across language barriers, but it works just fine for C to C as well. And that's actually how Wayland does its own internal dispatches.
Yeah.
You FFI the thing up. It seems like we should be able to use that for kind of making it so we don't have to have explicit entry points in libegl for everything that a platform extension might want to add as a new EGL function call. I'd like that to be true.
Yeah, I'd like that too, but yeah, I don't have a clear picture right now how we would implement that. Yeah. So far, the idea is to have this EGL external API specification, so external platforms can be implemented that way. This API can be extended in any way in a backwards compatible way. So yeah, libgl would continue to work with newer external platforms and the other way around if we want.
Okay.
So, any more questions?
Okay. Thank you very
Looks
much.
like I'm done.
Hey guys, please grab a seat. We are a bit late. Okay, sorry. You may start now.
Okay, no problem. Okay, let's get started. Yeah, obviously we're here to break the stream of NVIDIA presentations. We made that switch in the schedule because we hope that James' presentation is just a natural extension of our presentation. So we are Philipp and Lucas from Pengutronics, and we want to talk a bit about the challenges of using multiple DRM devices in one system. And yeah, the talk's title changed a bit. We had hoped to have some prototype implementations to get rid of those challenges, but time didn't permit that. So we basically want to give you an overview what the problem is and what we need to change. We want to make this a bit interactive, so if anything that we say where you feel that's wrong or you have some ideas about it, please raise your hand and let's talk about it. So the first thing that we want to make clear is that we need to get a clear split between Windows system integration and acceleration APIs. It might seem obvious if you're talking about OpenGL on X or Wayland or something else, but it gets less clear if you're talking about going bare to the hardware with Windows system integration that might be GBM. Where you're talking directly with KMS or DRM devices. EGL obviously is somewhere in the middle of this, bridging the Windows system integrations into the acceleration API world, so you can get an acceleration context on something that is able to present what you rendered or did accelerated. So in the classical KMS DRM world, we had a dev DRI card, whatever, and basically provided both sides from a kernel perspective. You could do scan out, flipping buffers, presenting them on the screen, but for devices like your graphic card in your computer, it traditionally also provided the render acceleration. This has been broken up recently with the introduction of render nodes and also control nodes, but they are not universally used yet. But we want to make that clear separation, because if you're talking about a system on chips, this separation is much more strict, because you don't have the single card whatever device, but you might have a card one device that's able to do the scan out, and so it's only the control node and doesn't provide any render acceleration. And you might have DRM devices that are only able to render something and not able to present something on their own. So what we would like to focus on is the classical use case of what a compositor has to do, compositing things with OpenGL, talking to the render devices, and presenting things with GBM as an API to bridge the OpenGL render buffers into the KMS world.
There's a question up there.
Okay. Right.
Like the difference between the control node and the normal card node is that with the control node you can do anything even if you're not master.
So it's usually...
Yeah, the control node is an unloved child. There is really a big inconsistency in the API of the control node in that it allows stuff that you can't do with the card node, but also it disallows stuff like prime handle import and such stuff that you would like to do with a presentation node, basically. Yeah.
I mean, just as a comment, but the general way we use it is to just say use the card node and don't use the control node. I think the only people who really use the control node are the BMW GFX.
The problem with using the card node is exactly that it makes it easy to break the clear separation of render and card or scan out if you're talking to graphics card devices that are able to do the same thing. Well, both things together.
Sure, but I mean...
Yeah, we'll come to that later.
I don't want to derail you too much, but I honestly don't think you can make that separation as clear as you're hoping if you have a presentation API that needs to be able to swap buffers and you aren't going to succeed at flipping. You are going to need to blitz. You are going to need to emit rendering commands. I know that doesn't sound like an acceleration API, but I don't think you have a clean separation there. I admire the desire to get one. I don't think there is one. I don't think there's one to be had.
If you're talking about the compositor side, sure. If you need to blit or whatever, you need to talk to an acceleration API to be able to do that. But if we're talking about the compositor that actually uses the compositing API to composite things and then wants to flip that on the screen, you must succeed in flipping. Otherwise, the compositor hasn't really done its job. At least that's what we have with GBM and page flipping on the DRM devices. Okay. So the first problem with GBM as an API or library is that obviously we don't have a vendor-neutral dispatch. So we run in all the same problems that we have with OpenGL or EGL. We need some separate instance. So GBM bridges to specific DRM scan-out devices. Those scan-out devices might not be all driven by a Mesa driver or some open source driver, but they may actually be driven by a vendor driver. So you need some specific instance of GBM that is able to talk to that driver. But yeah, that's mostly a solvable problem, as we can just do the same thing that GL vendor neutral dispatch does with the libEGL by saying, oh hey, I have a handle to a DRM scan-out device, please give me a GBM device, and the dispatch code just tries to hand it to the different implementations and until one of them succeeds, creating a GBM device on them. The much bigger problem for us, especially on the embedded devices where we really have a clear separation between scan-out engines and acceleration engines being driven by different DRM devices, is that currently, or the current implementation in Mesa of GBM mixes the windowing system integration parts of GBM and the acceleration context parts. I think you want to explain that.
Yes, I want to explain this. So, because this is a mental map of my current understanding of the layer starting from the Mesa setup for two separate devices that are using Gallium pipe drivers, and then the layer with GBM, EGL, and GL on top. So for the current the bigger cards that are using Gallium, you would have one Gallium pipe driver in the bottom that is talking to the dev card device, and then you would have the DRI state tracker and Mesa state tracker interfaces on top going to the layers above. But in the case that are interested to us because of embedded, we have the separate kernel devices for the render and for the presentation device, which is the display controller, which then seems to have to use dev card for this one, but for the render device we have the render node. The two pipe drivers are in the bottom completely separate. Just one of the pipe drivers, the one for the render device, implements all the render functionality, and the other just the presentation part. And then when you start building up your context on top of those, you first have GBM, which does the buffer management and presentation, which naturally would sit on the presentation device. So this block is painted on top or above the DRI state tracker with the GBM DRI backend to GBM on the display part. Then you have the EGL glue layer sitting on top of that with the platform DRM. Sorry, this is this is platform DRM sitting on top of GBM, and the EGL DRI2 sitting on the DRI state tracker of the render device to do the rendering blitting that is necessary. So we have, in theory, two separate devices, both used by EGL, and then we want to set up a GL rendering context on the render node. And what happens in practice, if we want to do this, is as soon as the context or the driver call, the call that is bringing up the context, the GL context, is passed DRI screen structure, which originates from the GBM layer, which is an abstraction for the pipe screen of the device that the GBM layer is sitting on. So this is obviously not a problem if the Gallium layer is just one device. So maybe it's a bit disingenuous to draw it this way, but it illustrates very well what is our problem here. We want to have a presentation layer on the presentation device, ideally, and then start from there building up the render possibilities. And at the moment, what we have to do is to somehow, at the point where we create the context, get to the render functionality. So there's the possibility to just give up and build a single Gallium driver for both of them, which would mean, oh, sorry, please.
So when you've been talking about GBM Windows system stuff, are you talking about the GBM Surface functions?
Yes.
Right. So why use those at all? X does GBM KMS rendering stuff, and it doesn't call them at all because why would I want that?
What else?
You use surfaceless, and then you grab your buffer handles and hand the buffer handles off to the thing that's going to actually do the presentation.
So Eric, I can answer that. Up here, the GBM surface was added because a lot of applications wanted to use a EGL surface in their loop when porting Qt, for example. An easy way to get that up and running was to have a way to provide an EGL surface, and then GBM surface lets you have a native surface type you can pass to EGL create surface, and you can pass the EGL surface to Qt. And then on the other side you can pull the buffers out of the GBM surface and get a GBM BO out of that. So that was basically the motivation for GBM surface.
Right. The problem with GBM surface is not that it's GBM surface, but that the GBM surface currently transmit all the context information of whatever driver is sitting below the DRI interface. So you have a GBM context that has a DRI display which has whatever the driver attaches to that, and it hands that to EGL, and the current EGL DRI2 implementation uses that information to try to set up the render context.
It still seems to me like you should be able to run GBM on the render node only, and your Windows system layer would talk directly to KMS. So that seems like the correct model for handling this multi-card situation to me.
The problem is how we'll come to that in the next slide. If you want to break that up, first the first issue is how to find your actual render device. EGL device, obviously, yeah.
I can answer that one. So, made a rather interesting looking helper in libtpl-egl. So it will give you a bunch of devices, and pretty much for everyone it will give you...
Do we have any correspondence between...
Yes, if your kernel driver is
render
same,
node?
It should give you a nice mapping between card and render nodes, and pretty much all the three.
Okay.
So just don't look into the implementation.
Okay, that's what I wanted to know. Okay, so that's the first issue, and the next issue is how do you actually negotiate buffer constraints if your scan-out isn't capable of scanning out what your render device would want to produce. So a relatively common thing found on embedded devices is the last point. So most GPUs have some kind of MMU before them, so they can just use paged memory, and our scan-out engines are incapable of using paged memories. They need large chunks of memory, and we don't want all buffers for the graphics to come out of or be allocated in large chunks of memory, because that obviously puts pressure on the memory allocator of the operating system. And other things like alignments, depending on where you allocate, or where do you want to allocate the buffers that you're going to scan out, you need some mechanism to actually transfer all those informations. So if I allocate from my scan-out device might have the only limitation that my that the stride needs to be aligned to 8 bytes. But to actually be able to resolve my buffer into the scan-out buffer, I need an alignment of 64 pixels or something. So how do you get this information across? If you use plain GBM with the buffer object ABI, with allocating GBM BOs and pushing them into the surfaceless MESA. I think we've looked a bit at the Windows system in implementation of the Intel Vulkan driver, and it has exactly the same problems with tiling.
So yeah, this is kind of a big problem, and there's a partial proposal that's kind of on the table, which I think James is going to discuss in the next talk, to solve exactly this problem. Namely that we need to be able to have negotiation of tiling formats and strides and formats and various other things in order to work across components, and even to work within the same component of the graphics stack. Like on Intel, we could be making better choices about surface allocation if we know whether or not it's going to be scanned out, or whether you're just going to composite from it. So yeah, this is a big issue, and I think we're going to have a lot of discussion about that this week.
Right. And I think the Surface API from GBM is actually helpful for the negotiation, because you can... No?
See, yes and no, right next to each other.
Okay. It's different reactions from the audience. So, yeah. So anything that we're that we might be missing here in our list of things that you might want to negotiate?
Yeah, basically all of the negotiation is missing right now.
Right.
Like, the way that we're doing it, the way that I think most people are doing it who are working within sort of the Mesa open source framework, is that you just always do what you know you can guarantee can be scanned out from. And if it turns out that...
I'm maintaining the Edna with driver.
So
I have no idea.
You're in a scenario where you
don't
don't know what you're going to be able to scan out from, and that's an even bigger problem. But like, even on hardware where we control both the 3D and the scan out, we just sort of make assumptions and hope it works. And when you're working on two different devices that may be made by completely different manufacturers that don't talk to each other, you're just sunk.
That's our situation right now. Yeah, it's pretty accurate.
So for the format negotiation, have you looked at what Video for Linux guys are doing in a media controller framework, where they have the same issue where they need to hook up like a hardware video decoder to a frame buffer or whatever? Because the media controller framework has this elaborate way to describe actually between sinks and sources of buffers all the formats parameters.
As I understand, is you have a framework of entities with paths and sinks that are somehow connected to each other, and then you can set properties and formats on those paths and sinks, and the drivers in their link validate callback, I think, can veto changes with the error message or with the error return.
Yes, that's correct.
So
yeah, there is one problem with it, that since if you look at hardware video encoding, decoding, and pipelines for things like camera sensors, the pipelines are so complex. If you take image signal processing, which is also in the pipeline, to account that there is no in-kernel negotiation. The idea is that there is a user space library which knows the hardware, and that's all the kernel does is just make sure that what the user space is setting up is same. It doesn't do the negotiation in the kernel, at least that to the user space.
The way I understood it, this is mostly about the formats of the contents, or in case of hardware, the format of the data on the wire.
Yes, that's correct.
But I'm not seeing how this can help in this case, because here it is about the layout and possibilities of alignment of the buffers that we want to share.
Well, for one, you also want to negotiate a pixel format, right? You want to both be in 32-bit depth or whatever. And Video for Linux also has not only serial links between dedicated hardware blocks, there's also cases where the data is being moved to and from memory buffers. So that's in there too.
Yeah, but most of the negotiation part in Video for Linux is actually taking place in user space in frameworks like GStreamer or whatever that are able to probe the hardware elements and then negotiate some common denominator. So that's probably the thing we want to have, and I think it's impractical to have that in the kernel or somewhere below the user space interface. So yeah, the place to add that is probably for a first shot to get it running inside Mesa, because we can change interfaces there and prototype stuff between different drivers. And after that, we would have to extend that to make that negotiation across the wire for Wayland compositors and clients to negotiate what buffer formats, format modifiers, and whatever they need. And I think GBM is actually a pretty good target to prototype that, because you have all those interfaces internally inside Mesa. So, okay, I think there's a common understanding of the problem space. Okay, and once you have that negotiation in user space and you know exactly what buffer you want to have, one of the bigger issues is where do we actually allocate that buffer? Because most of the hardware drivers are only capable of allocating buffers that are suitable for their hardware. So most of the hardware drivers that are dealing with capable GPUs that can use page memory just don't bother to deal with contiguous memory. And what if you ask this driver to actually allocate a contiguous buffer? Where do you get that buffer? And I think that's one of the things that James wants to talk about. So, any questions for this?
Or violent opposition? Not yet, okay.
Yeah, not so much a question as a remark. If you're going to work on all this negotiation stuff and also the allocating stuff, the video for Linux guys, the media group really has the same problem. Because if they have hardware video encoding, decoding, and it goes to memory, they also need to allocate a buffer which they can share. And it would be really nice if... What? Yeah. And it would be really nice if you could talk to them and try to get them involved, because in the end what we really want is that you can also negotiate a buffer between a hardware decoder and a scan-out engine, so that you don't need to do a blit in user space there, especially on embedded systems which lack the memory bandwidth to do that blit. So since you're looking into this anyway, please keep the media guys in mind, basically.
Thank you for the remark. Since we regularly have to implement video use cases, we will stumble over this eventually. So.
I don't know if you have any slides talking about it, but do you also face coherence problems with the different engines that you're working with?
Not really. The caches on our render engines are small enough that we can afford to flush them after the rendering without sacrificing too much of the performance. Okay. So we just flush them to main memory and then we are coherent. But yeah, that's also a problem about when to flush a resource, actually. Bigger issue for us is that we actually need to do a blit from tiled to linear, because our scan-out engine on the IMX can only do linear.
One version of the IMX?
Right, the next version will do tiled. But yeah, you basically want to do that blit as late as possible, and you know rendering finished and everything's okay. So yeah, same thing. Okay. Up to the next talk.
go to
Okay. Can everyone hear me? I'm going to get started now. Is that better? Okay. If anyone hasn't met me before, I'm James Jones. I work at NVIDIA. I've been there for about a decade now. I'm working on Windows system integration the whole time, so it's been a great career so far. And somehow it's all led to this. In the last couple of years, I guess everyone's been talking about doing Windows systems besides X. So for the first 5 years or so, it was just X11. Now that everyone wants to do their own windowing systems or alternative ones, a recurring set of problems that come up about how we go about handling the memory allocation for that, and other parts of that were previously entirely handled inside the driver. Obviously, there's some solutions that are out there already. As we were going to try to bring a solution to the NVIDIA driver, we noticed that there were some problems with those solutions that we're trying to solve. The first thing we came up with is EGL streams. It's not so well received so far, but I think we'll go over the reasons we presented that as a solution, the benefits it has, as well as the positives and negatives of some other solutions that have been put forward. And most importantly, we'll talk about like where do we go from here. So the whole discussion started when Miguel sent out a bunch of patches that added the EGL device and EGL stream paths to the Western backend, or the Western compositor for Wayland. That quickly turned into a debate of EGL streams versus GBM, which is fine. It's a good debate to have. There were many strong views expressed there. Obviously, there's a lot of time that's been invested on both sides, from the NVIDIA developers doing EGL streams and from everyone here doing GBM. So given the strong views held and the emotions involved, thanks for keeping the discussion civil so far. It's really great to have a purely technical discussion on a really contentious issue, and I thought it was great.
Can you try moving the mic, because it keeps... Try that here.
Does that sound okay? Great. Okay, so as I was saying, thanks for keeping the discussion civil so far. It was great to have a really good technical discussion without getting into a flame war. I think the important part of those discussions was so far we've identified many areas that we can improve in the allocation mechanisms that exist right now, be they streams or GBM. The discussion itself on the mailing list kind of died down, so it was suggested that we pick it up here. We'll probably have all the right people present, and we got good attendance, so hopefully we can actually solve some real problems here, discuss those problems and get some solutions. To start off, the problem space we're talking about is basically how do you create device-accessible surfaces where devices is, GPUs, scanner engines, video encoders and decoders, using some API and user space. That's the most basic part of it, I guess. Beyond that, you also need to be able to create handles for those surfaces so that you can access them across process namespace boundaries. So if you want to have security between your compositor and your client applications, obviously, you have to have some way to get these buffers between the two applications that's secure, and that shares all the information needed about those buffers as well with those handles. Something that's come up more recently as things like Vulkan have been released is the idea that you have to be able to manage the state of those surfaces as you use them. So this was touched on a little bit in the last presentation. Do you have cache coherency problems? Yeah, we do, even if other people don't. And beyond that, there's also the idea of people doing color compression and the need to be able to turn that off when you're talking to different engines that don't support it, as well as a couple other things that just get bundled into the idea of surface states or surface layouts. And then when you're sharing these surfaces across multiple devices or even multiple engines, you have to have some way to synchronize them as well. And that's not a directly related problem, but this is worth keeping in mind as you're talking about these other parts. So what I'm doing now is I'm going to give a background, basically, of what has been discussed so far, in hopes that it prompts some more discussion where we can actually get some solutions. So my goals for the XDC conference as a whole is that given the people we have here, we could work on developing a consensus-based forward-looking API for surface allocation. I mean, what that API is, you know, it could be anything, but I think the idea is to come to consensus on what will work for everybody as a set of features, not necessarily an API name. If it's GBM, it's GBM, you know, 2.0 or whatever. It's fine. I think it's important that the API be like Windows system, kernel, and vendor agnostic. So I don't want to just be solving Wayland, or I don't want to just be solving, you know, Android. I want to have some kind of solution that can be reused across any number of windowing systems, or even for embedded use cases that aren't windowing systems necessarily. I just want to stop having to write this API every time we get a new customer that wants to do something that's not X. As far as across different kernels, that would mean probably old and new Linux kernels as well as non-Linux kernels. We have a lot of people trying to do things on, you know, not Linux operating systems, but they are POSIX or POSIX-like, so it seems like the same solution should apply to all of them. And again, just being, I don't want to keep rewriting this every couple of years just because we have a new operating system come up. So since we should be working on some kind of user-space API, it's talked about in the last talk, it should make sense to at least try to make it not Linux specific. And obviously vendor agnostic. I think any solution isn't going to be very good if we can only use it on one vendor. Ideally, there'd be a minimal but optimal driver interface for the API. So it's good to have an API that's as small as possible, but we want to make sure that we can use 100% of the GPU's capabilities in that API. And then not directly related to the surface allocation problem right now, but we should keep in mind that the final destination should be something that enables us to build a completely optimized scene graph for something like Weston or any kind of scene graph compositor. So that means we should be able to make every frame, well, in the steady stage, be able to get to a case where the frames are being composited in a way that is the fastest possible way on that given GPU and system configuration. So I'm going to go through a very brief overview of some of the prior art in this area. Obviously, everyone here is pretty familiar with GBM, probably a lot more so than I am, and probably a lot of the other things as well. So I'll try to go through this pretty fast. Feel free to correct anything I have that's incorrect on here. So at a basic level, GBM provides a method for allocation. It has some basic way to arbitrate different usages of surfaces via like usage flags, and it provides handles to those surfaces. Some of the benefits that GBM has is that it's incorporated in many code bases now. Obviously, half the presentations today have been on things related to GBM, so it's been widely deployed and tested. It's a pretty minimal API, and implementation is fairly small as well, at least in the implementations that I've seen so far. And it does have allocation time usage specification for supported usages. So if you want to use scan out or render target stuff, you can specify that when you allocate the image. The current shortcomings are that the handles it provides are process local. It has some methods to import handles, and I think there's indirect ways to export the handles, but there's no GBM call to say export handle as far as I know. It's currently very GPU focused in that I think the capabilities it describes are basically rendering, texturing, and display. So if you wanted to describe a way to render and then use a surface with your video encoder, that wouldn't be possible with the current GBM flags as far as I know. And kind of related to that, the arbitration between the different types of capability you need for a given image is at device scope. So kind of what the last talk was saying, if you want to say allocate an image that's capable of being used with 2 devices, GBM doesn't currently have a way to describe that.
we can export GBM buffer and send to another process as a prime, and we can import now.
Right, but I guess the mechanism to expose that handle is not within GBM, right? It's like a prime buffer or something like that.
It's just a DMA buffer.
Yeah. Yeah.
I just had the same question, me and Zach, but I think the problem is the exported prime FD doesn't have any real metadata associated with it. And so if your buffer is anything but incredibly simple, that prime FD isn't enough when you import it into the other client. It's not a true export.
Yeah, so there's some export capability, but it's not as complete as we'd like it to be, I suppose. Sort of an add-on to the GBM prior art. There were some efforts with Chrome OS Free on development to add some kind of surface state management to GBM, or on top of the GBM API. We wanted to be able to do stuff like, say, take this image that was being used in OpenGL and transition it to be used for scan out, or to be used for video encoding or something like that. There was a lot of discussion there between various vendors, but we failed to reach consensus on an actual optimal design. I think we ended up falling back to something not ideal. I stopped working on the project, so I didn't see the final outcome. But one of the major points of contention that's worth noting there was we couldn't agree on the level of abstraction that we wanted for the description of the transitions themselves. So that might be one of the things that we end up discussing while we're here. Somewhat similar to GBM, but I guess also with broad deployment is Gralloc. It provides roughly the same kinds of things that GBM does: allocation, arbitration between different usages, and surface handles. It has some synchronization stuff in the Gralloc API via the usage of Android and Linux fence FDs and a locking mechanism related to those. And there is the ability to use Gralloc handles across processes using some other components in an Android system. But again, they're not directly in the Gralloc API itself. So it has roughly the same benefits as GBM as well. It's widely deployed and proven in the field, and obviously I think a lot of us have phones using it right now. It has allocation time usage specification, and it does include things like video encoders and decoders. So yeah, and it has some support for non-graphics usage. The shortcomings are also similar. It doesn't, that I know of, have explicit surface state management in it right now. It could be done implicitly, I suppose. We've done that in the past, I think. It has limited usage flag-based arbitration abilities. So I mean, if you can't express it with a bit, basically it can't be described. And it is open source, but it is a somewhat proprietary API, and then Google ends up controlling it in the end. Prior art is VGL stream. Given that it was more or less developed to solve the problems we're talking about here, it does solve most of the problems. It provides allocation, arbitration, provides handles that can be shared across processes, has state management, and it has synchronization built in. And the benefits are, it's been proven in the field. We've been shipping it for quite a while, and a lot of different use cases. I guess it's not as broadly deployed as GBM or Gralloc. It's very portable. We ported it to pretty much every operating system we've come across. And it has a very comprehensive feature set, like I was saying. The shortcomings are that while it's an open standard, in practice it only has a single vendor implementation. We haven't seen anyone besides NVIDIA that supports it so far. It doesn't currently have cross-device support. It's EGL based, so if you're trying to do something that doesn't want EGL involved, too bad, it brings EGL into the picture anyway. It's been said that it has too much encapsulation, and that it tries to do too much within the API, things that are not directly related to the problems we're trying to solve here. And I've been told that some of the behavior is too loosely defined, or it tries to bring things into the API without defining enough detail about how they operate, such that there's some loosely defined cases. So yeah, one of the other examples of prior art is DMA buff. DMA buff is basically just, as far as we're concerned, user space, a handle. So it's a way to describe a memory allocation from some driver and share it between drivers and between processes. The benefits are that it can basically support any kind of driver, and it has the ability to be shared across processes via file descriptors. But the current shortcomings are there's no single user space API to allocate DMA buffs. There are a lot of user space APIs that can be used to allocate a DMA buff, but it's not clear which one you use for a given situation. And there's no centralized way to say I want to have a DMA buff that works across these various drivers. As far as I know, it's currently Linux only. It doesn't describe anything about the content layout, so it's just a raw piece of memory. There's no user space way to arbitrate between different usage cases. And in fact, there's no way to say, like, given that there's a bunch of different allocators, there's no way across all the different usages to say I want to have these particular uses for this buffer when I allocate it. Obviously, if you allocated a DMA buff through GBM, you could use that API's usage specification stuff, but a DMA buff itself doesn't have a usage specification or arbitration capability. Vulkan is interesting to consider in this space as well, in that it does provide surface allocation and has I think it's the first API to have really detailed usage specification at allocation time. So when you allocate a Vulkan image, you need to say exactly how you're going to use it for the lifetime of that image. And that allows us to make very, very detailed optimizations in the driver about how we choose our image parameters. It has very explicit state management. So every time you want to change how you're using an image, even when you're just doing between different images in the GPU, you have to make sure you do proper transitions between the states on the image itself. And it provides a robust explicit synchronization mechanism as well. So the benefits are, it has all the features I just talked about. It's also very extensible and very portable. It's not tied down to any particular operating system. The shortcomings right now is that there's not currently any cross-process or cross-API or cross-device handles or sharing, or arbitration of usages. And currently it's focused on graphics and compute, and also on the side display only. So it's also a very GPU-focused API right now. So the point of going through all these APIs is that we've identified a bunch of features that are either common to them or commonly missing from all of them, or many of them. I think we can agree that it's important to have a minimal API. We don't want anything in the driver that doesn't have to be there. It's important to have portability, so that whatever API we can come up with can solve the problem across a variety of platforms. It's important to support non-graphics devices, as people were saying. Everyone wants to render to their video encoder. Everyone wants to texture from their video decoder. So we need to be able to support things that aren't GPUs. I think an important goal is to have optimal performance in the steady state. So if someone's not moving windows around the screen, we want to make sure we're using the GPU in the most optimal way possible. And right now with, like, for example, X11, we can make sure we turn everything on the GPU that we can when the window's in a steady state and get really great performance. So I want to make sure whatever we design here can be at least as good as what we're doing with X11 right now, or otherwise why are we working on other systems in the first place? To achieve that, I think we really need to have something along the lines of what Vulkan has in allocation time usage specification. So when we ask the driver to allocate an image, we need to know upfront all the different possible use cases it's going to have. And then once you know the usage cases, we need some way for the drivers to negotiate the image capabilities. So given a set of usages, the drivers want to be able to say, okay, I can do that using these capabilities in this optimal sorting order. So while the optimal use case in the steady state is important, it's also important that we don't fall off a cliff when someone moves a window or someone goes from full screen to not full screen. So it's important that we're able to support multiple usage cases with the same image without reallocation. So we don't want to fall back to like a black screen or doing really slow blitz every time we have to switch states. So along those lines, I think it's important to have image layout transitions, so we can say, take this image that was being used as a texture and start using it to scan out instead, preferably without doing any reallocation. So we have these various APIs. I think there's some more or less consensus goals that we're working towards. There were some consensus ideas of what we needed to add on top of all the existing APIs to make them all better. So as a path forward, I suggest we focus on solving the specific problems that we have rather than picking a winner API right now. And I think as we solve those APIs, as we solve those problems, it will become clear what the API should look like, and then whatever it's called isn't really that important. Specifically, I think we should focus on solving the problem of being able to create a surface that's cross-driver, cross-engine, cross-device first. This has kind of historically been where everyone kind of gives up and says this is too hard. And if you solve this case, all the simpler cases fall out of it naturally. So if you create an image that's usable across 5 different devices and 2 engines and 2 different driver stacks, then you can obviously create a device that is usable across 2 different engines on 1 device. So if we solve the case of rendering to your video encoder, we can probably easily solve the case of rendering to your display. This doesn't really take into account the case of state transitions, but state transitions are a lot easier if you've already solved the idea of describing exactly what your capabilities are in that image. And another reason to focus on this particular problem right now is that Jason Ekstrand has written up or developed some proposals for how it would look. And I've tried to summarize some of those later on the following slides. So some assumptions that I've made that I think are useful to keep in mind when you're thinking about these proposals at least is assuming we're designing an ideal allocation API from scratch. So that doesn't mean that we actually are. What I'm talking about is not burdening yourself with backwards compatibility for now. Think about the optimal solution and then try to adapt that solution to whatever we're going to plug it into. I think we should think in terms of a user space API first, in that we should be thinking about what an application is actually going to call. Obviously, there might be some kind of kernel changes or kernel APIs behind that to actually do the allocations, but I think for the part that needs to be portable and usable across platforms, we need a user space API. And finally, both API elegance and hardware capabilities are important. So, and it'd be great if we had an API that was only 1 entry point called alloc-image. But we also need to be able to be sure that we're actually using all of the GPU silicon that we have, and other silicon as well. So let's not waste hardware capabilities by not exposing them in API. I want something that's actually optimal as well as elegant. Okay, so getting to the actual ideas of how we could create a mechanism for sharing images or allocating images that are usable across devices. I guess the main problem is that different devices have all these different tiling formats and imaging quirks and everything that are specific to their driver, specific to their hardware. And the other drivers aren't going to know about them. So I think what we need is some kind of common way to describe those things such that when you're sharing things between 2 devices that are compatible, we can get the most optimal format between those 2 devices without losing the ability to create allocations across devices that aren't compatible. So I think that requires some kind of standardized way to describe the capabilities. So for those who have seen it, this could be similar to the Chronos data format spec, which creates a standard way to describe data formats, but then also allows you to extend it and add your own kind of capabilities if you have some new kind of data format. And then if you don't understand those new data format capabilities, you can just ignore them and still use the basic format. And it's just not quite as specialized as the full format is. So once you can describe these capabilities, you could be able to query a list of them from each driver. Those lists could be really large. For example, I think on NVIDIA there would be no way to fully enumerate all of our tiling layouts because they're kind of arbitrary. So what you really want to do is query a list of capabilities given some particular usage case. And since we have some kind of driver-specific capabilities and some common capabilities, we need some central authority that will mutex the capability namespace. So we can't have NVIDIA using a capability that has the same identifier as Intel driver, for example. So we need some place we can kind of say this format means this and check it in and make sure no one else can clobber it. So I don't know if that's like just a file in a Git repo Or if we want to get Kronos involved and say Kronos can be the person who hands out these IDs, or whatever. It can be anything as long as it's authoritative. So that once we can get a list of capabilities from all the drivers involved in a given allocation, we need some image creation function that intersects those capabilities in such a way that you get a list of only the compatible things from all the drivers. At that point, you have the list of capabilities that you can use for an image that can satisfy all the use cases you want. So how are the capabilities filtered? So you should filter based on the usage. Usage could be things like format, the operations you're going to perform on the image, the dimensions of it, and obviously the engines on the device that are going to touch it. And that leads to the next question of how do you describe usage? For some things, there's obvious representations. You could use the Kronos data format spec for formats, and it's supposed to be able to describe a superset of all formats that exist. For width and height, I mean, obviously some kind of integer is pretty clear. Other things can be Boolean flags. Sometimes you can say scanout's a Boolean flag, whether or not you're going to scan out or not. Sometimes it's not so simple. Sometimes scanout can be a whole set of flags. You're going to scan out rotated, you're going to scan out mirrored, you're going to scan out on 2 different planes simultaneously. So it needs to be some kind of extensible method that you can use to describe the usages. We should do it in such a way that each driver can ignore usages, target only at other drivers. So there should be some way that says I want to scan out, but only on the NVIDIA driver, and I want to render, but only on the Intel driver, or vice versa. So then each of those drivers should be able to ignore the usages that are not targeted at their particular driver. On the other hand, you have things that are going to apply to all drivers, so we should have some way to say I want to be able to perform this usage on all the drivers that I'm talking about. So once you have a list of capabilities, you need to have some way to intersect them. And I mean, it's easy to perform a basic intersection where each driver goes and eliminates everything that it's not going to be able to support at all. I think the harder part is once you have a list of capabilities that can be supported on both sides, how do you pick to the optimal one across both those drivers? You could have the case where you're left up with 2 capabilities or 2 different tiling layouts, where one of them is optimal for the renderer side of on one driver, another one's optimal for the display side on another driver. Assuming those are 2 separate drivers, who's going to do that sorting? It's not exactly clear how you do that or which one's going to be better in the long run, since they don't really know what each other is doing. And only the application really knows what it is doing. So it might be doing lots of rendering, and then how optimal scanout is not that important. Like it's willing to burn a little bit of power to get higher performance rendering. Or it might be more optimal to save power on the scanout because it's doing very simple rendering, like just clears and quads or something like that. So the first proposal is to use the app-provided sorting. So if the application said these usage cases are provided first, then use those as the most important ones. So satisfy that requirement first. Another way to express that is to let the app specify this is the primary device that I'm most worried about. So once you've actually decided which capabilities to use, there has to be some way to describe them in a cross-driver way. It's not clear if that can be the same mechanism that we use to describe the capabilities themselves, since some of the capabilities might be in the form of ranges. But ideally, we could do something very similar or exactly the same as the capability descriptors themselves, and kind of associate them with that image handle, and then pass them to all the drivers so they know what they're talking to when they have to actually render to or read from that text image. And I've been talking about only image capabilities so far, but images are mappings of memory, and the memory has its own set of capabilities. So there's things like contiguous memory for old devices that don't understand page tables. You might have things like they're talking about in the last talk, like stride alignment, offset alignments, and everything like that. My hope is that that's roughly the same problem, and it can be solved with kind of roughly the same mechanisms. I don't know if it's actually done in the same step or a separate symmetrical step, But I think once we solve the image capability problems, we probably have this problem solved pretty quickly as well. Let's see. Any questions so far? Did any of that make sense, or did I go over through it too fast?
Do you already have a list of capabilities that you would have gathered across a few devices?
Say again? Sorry.
Do you have a list of capabilities that you would have gathered across a few devices? Just, you know, we're talking about how to express capabilities, but well, some that are quite obvious, like do we need physically contiguous memory or not? But would you have a bit more exhaustive list of what you have come across so far?
Yeah, some of the ones I mentioned in examples so far are just things like the tiling layout that like a GPU would use, whether or not they're using any kind of hardware-focused metadata like compression on the hardware. Yeah, things like that.
One we could add, I've seen on the camera side, but obviously if we have an image allocator that should handle buffer sharing between different kind of devices, is planar formats like NV12, where the two planes have to be allocated from different physical memory banks. So that's quite device specific, but there's a kind of corner cases that makes it difficult to create a generic API.
Yeah, so I think that would be the kind of thing that would be expressible in the memory capabilities type stuff. And ideally they'd be generic enough to describe anything, because I'm sure we're not going to think of all the different things people come up with in the future at the forefront. So that's why I think extensibility is an important capability, important property of the API.
On the prior art section about the, I think the Chromos Freon GBM extension thing, you said you had some discussions about like the arbitration, the level there. Can you give some more details there? Because I think I've not seen that discussion.
I think that some of the disagreement was, this was a while ago. I think this is the idea of should we specify that I want to be able to like scan out on this particular device, or should we just say that I want to scan out, or should we say that I want to put the image in this exact state, where that state is a specific thing to that particular device, you know, that particular revision of that particular vendor's kind of GPU or something like that. I think it's important that we have an API that the application can use across a large swath of devices without rewriting the application, such that it's optimal only for a very specific device. So I mean, I want to be able to release a new GPU, plug it in with an old app, and have that app still run more or less optimally. You know, maybe not 100%, but pretty good. So I think the level at which you expose your states and which you expose your capabilities and everything on the application side has to be at such that it's abstract enough that you can still get that property out of the API. I think there was disagreement over that being an important feature. Okay. At the end of my slides, I have a couple more slides here that are some pseudocode for an actual API to do some of this. I'm not going to talk through all these right now, but I encourage people to look through them later on if we post the slides online. I think Jason also has some code that he's working on that sort of implements some parts of this. Okay, well, some ideas written down maybe, or ideas in his head. So I think the idea is that we'd use some of the ideas presented here. Oh, go ahead.
James, one question that I have is that in talking about this, there's been like the idea that instead of having like one allocation API like GBM, once we have the ability to talk about capabilities and requirements, and we can communicate the result of an allocation also in a generic way, we don't necessarily need something like GBM or Gralog or anything like that to be around. We can collect requirements from different consumers, and then we can pass those requirements into Vulkan or OpenGL, and then allocate a buffer that way. And then so what the allocator becomes a GL extension, for example, or a Vulkan extension. And the other thing is that when you do it that way, all the knowledge that you need to have about the different capabilities can be in the driver, where it's kind of belongs. But if you have one allocation API, that allocation API has to know about all the different requirements from all the different potential consumers.
Yeah, I think whatever allocation API we do use should have a driver component. It shouldn't be the allocation library's job to know that NVIDIA has these 40 formats and capabilities and everything, and I know how to use them. That should be dispatched to a driver in the back end. So when I say API, I really mean some kind of vendor-neutral dispatching thing that is able to talk to various drivers. That could be Vulkan, it could be EGL.
But what I was thinking was, if I know that my producer is going to be Vulkan or OpenGL, then I could collect those requirements from the different consumers, and then have an entry point in my producer API, so say Vulkan, that because it has to produce the buffers, it knows the potential types of buffers and layouts that it can render to, and it can pick the best that it knows about from what I give it. So that way, we don't have to have a dispatch mechanism or a generic API. We can just go to Vulkan and say allocate a buffer, and then turn around and use Vulkan to render into that buffer.
I mean, that works great as long as the only thing touching that is things that Vulkan knows about, right? But how does Vulkan know to optimize the capabilities for a video encoder?
Right, but ultimately, Vulkan needs to be able to render into the format that it chooses, so it has to know about the format it ends up picking.
It has to know about the format, yeah, but how does where do you get the capabilities to say that the video encoder can only encode from linear formats?
You would get that from the encoder. So I mean, the negotiation process would be that you talk to the different consumers. So maybe there's one, maybe there's multiple consumers. So you'd ask those in turn, what are your requirements, and then you would take those requirements to the producer, and then say Vulkan, and then Vulkan would then pick the best possible from what the different consumers can consume.
Yeah, I guess the problem you get into there is what I was talking about before, where is the GPU the one that knows best which one is most capable? In a lot of cases, it probably is, but you could say you want to be able to render to something that's encoded by 2 other video encoders. Maybe one of those video encoders has a better idea of what's optimal out of a couple of formats that it supports for that particular usage case. So you could say that, okay, in that case, get the capabilities from Vulkan and allocate it on the video encoder. And maybe that's what you do. It might be that what we're describing here is just a set of metadata that you can pass around. That could be the API. But it might also be helpful to have some kind of, depending on how you describe it, lower level or higher level API that does that process for you of collecting those capabilities and passing them into some driver to form an allocation. So you could call it an helper API or whatever, but yeah, I'm not sure if that's going to solve the problem just by using, just by forcing the application to go and do that actual process.
Okay. Yeah. So it wouldn't just be Vulkan. Like if you have another producer, like you have a video decoder, that decoder will also know how to allocate its buffer, and it would know how to consider the requirements coming in from the consumers of that buffer. So the idea is that there isn't one allocator. It's not like Vulkan's the allocator. It's not like GBM or Gwangyeong is the allocator. Multiple APIs can have entry points that can allocate buffers and can import buffers, considering these the metadata. But the idea is that what we're talking about isn't one API. It's a set of capabilities and formats, and so we can talk about requirements and negotiate across APIs.
Yeah, I agree with that, but the whole point in this is that we have multiple drivers that can do allocation. And we eventually need to pick one based on the different constraints. So yes, we can have GPU drivers, we can have display-oriented drivers, encoders, camera drivers, but the code that gathers the requirements and then decides where to allocate and how to allocate should be kind of agnostic of whether we're using that on the camera side and display side, because we could certainly do that on a system without a display, so without a vulkan-wsi-tizen implementation.
Right. Well, ultimately, the producer is typically where you want to allocate, because you have to have a format that the producer understands. So there's only one producer. There may be multiple consumers, but there's only one component that produces
but
the data.
sometimes it's going to be the consumer that will have the constraints that are hardest to meet. While the producer can use pretty much any kind of memory, has an IMMU, for instance, while the consumer doesn't.
Right. But so the idea is that the overlaying, the compositor or some higher level component will ask the consumer, what are your requirements?
Yeah.
And then you get that really strict set of requirements from the consumer. You pass that to the producer, which then takes its own capabilities into account and the very strict requirements from the consumer that it's working with in this configuration, and then it'll allocate a buffer that works with that very picky consumer.
But so I think it goes both ways, right? I mean, the producer is going to provide capabilities, which could include the formats that it supports, and the consumer is going to provide capabilities, and I think the only important part is that those capabilities get intersected, and if you get a non-zero list, you can allocate something that supports it.
Yeah.
You should be able to allocate it from either side because they both have the same information.
Right. And I don't want to say we have to do it one way or the other. I just didn't want to say that we have to have like the one central allocator, because I think this opens up for a model where you can have multiple allocators. You can have an allocator in Vulkan. You can have an allocator in a video decoder. Anything that understands these capabilities can be an allocator and export the buffers. And I think it's pretty powerful and a decentralizing feature.
Yeah, there's trade-offs both ways, I think, because there's advantages to that, but then the disadvantages, you have to go and add those allocators to every API that you want to possibly allocate something. And that's just a trade-off. You have to either way have some way to import things from a central allocator to other APIs. So there's work in every API either way. But I guess the counterexample to what you're saying is, what if you have an application that does a lot of different things but doesn't have to do all of them? So I mean, like the compositor, for example, it could render to a display engine, or it could render to an encoder. It'd be nice if it could allocate images using one central API, regardless of whether the system has both of those. Maybe it's just a small detail because it could use DLOpen as a solution to that. But I think it gets more into aesthetics. I think both of those designs work, and it's worth discussing.
So, setting aside the issue of should we introduce a new centralized allocation API versus do we shove it in all the client APIs, I have my own personal preference. I'll set that aside. Despite whichever one of those two choices we choose, I think I would really like to see this entire thing based around negotiation between the components in the system. The different components negotiate what the capabilities and properties are they support. Can you talk about that? I don't see evidence of that in this slide. Maybe you do that in a different slide?
Let's see. Okay, so this is a very simplified example of what a HAL API could be for the back end of this allocation API. So yeah, I think it runs through the various steps that the application-facing allocate image would run through. So the application would supply the usage, and the driver backend would take that usage and convert it to capabilities, filter those capabilities, and then allocate an image based on those capabilities. So it has this capabilities function that you would pass the usage and you would get back a list of capabilities. Once it would run that on every driver that was specified in the capability or on the usage list. So if you specified 5 different devices, it would call this function 5 different times. And once you have that full list of capabilities, you could filter them using this next function by passing that same list of capabilities back down to all the drivers and having them filter out everyone that they don't support. That should leave you with hopefully a non-empty set of capabilities that then have to be sorted. And sorting could be done as part of the actual allocation call, or it could be a separate call.
Sounds like you're describing a negotiation and filtering process that happens solely within the new API implementation, and the negotiation and filtering happens among the driver backends in the API implementation.
Right.
Okay. I was envisioning a mechanism where negotiation actually happens between the components, where the user-facing API would provide enough API to query the capabilities, send the capabilities over the wire, over to a different process, and that component could also participate in the negotiation by filtering those capabilities, maybe doing a filter, adding some more, and then shipping that across the protocol to a different process. And so the negotiation would be explicit among the users, but you want to hide it within the new API, in the library, basically, what you're proposing.
Yeah, I'm not set on this design. That's an interesting use case as well.
I'm not set on mine either. It's just what seemed natural to me.
So that's a good thing to point out. I think we did talk about that when I was talking about this with Jason and Daniel before. One thing you have to be careful of, though, is if you do that, do you let the actual application itself filter the capabilities, or you still pass those back into a driver for filtering? Because the capabilities might be such that the application can't actually understand them all.
No, I wanted to keep all of the capabilities and properties mostly opaque. And so the component wouldn't actually, the application wouldn't dig through all the capabilities and understand all the details. It would rely on the provided API to do the actual filtering.
Okay.
The application or allocator might not also know the actual usage on allocation time. So it would be good to have like a convert or split API between two usage models in case you need to reallocate later.
So I think the split is outside the scope of the allocation API. You'd have to have some kind of split capable device to do that. So that's going to happen on a specific device. So I guess my assertion would be that if you're going to need that use case, you should make sure you include the BLIT capability in one of your devices, and you use that device to do that BLIT later on when you have to. And then the application would be the application's responsibility to perform that reallocation in BLIT itself.
So I just want to add, I wanted to preface what I said before, that I think it was a very good analysis of what's out there and what this problem we want to solve, and I think most of the goals are right, and I think that this is very encouraging. So I think it's a really good start for this discussion.
Yeah, and thanks to Martin for pointing out that this is a good place to discuss it. I think it is. I think we're running out of time for questions, but I wanted to point out that the idea of this presentation was to kind of give a background and start a discussion, but we wanted to continue that discussion tomorrow. So far it's been proposed that we go to one of the breakout rooms upstairs in the elevators down there, go to the 6th floor apparently. Today? Right now it might be good to go over beers maybe then or something, or yeah. Okay, well I guess more importantly, if you're interested in continuing the discussion, I guess congregate down here after my talk and we can kind of meet up and see who's interested and decide on when to do it and where. And yeah, let's make use of the time we have together here to solve some of these problems. Thanks a lot guys for listening and for the feedback and everything.
I think it's time to wrap this up.
Yeah. So, thanks guys.
Thank you. Okay, so this continues next morning at 9. And the live stream, of course, also.